Okay, continue. My name is Silvia Hastraneda. I'm working in Technical University Eindhoven, and since recently I am also playing the role as a principal scientist in Eindhoven Institute for Energy Renewable Systems. And yeah, I'm working on molecular simulations for energy systems, energy storage, but any energy systems related to energy applications. And because we started with organization issues, I will like to encourage you actually to use the chat box. We missed right in these online conferences, the social contact, but I realized in the last days that the chat can actually function for putting extra questions that we are not, we don't have the space actually in coffee breaks or something like this, or to exchange email addresses or ideas or something. So please feel free, or put questions that we can address after the talks or during the talks. So please free to use this opportunity. And I will stop now because today we have a long morning, I would say, like this, and with we will start, and I'm very happy and delighted to welcome Professor Carsten Reuter, a leading expert in molecular modeling and simulation of catalytic systems, and the director of the Fritz Haber Institute of the Max Planck Society in Berlin. Professor Reuter held the positions previously in theoretical chemistry at the Technical University of Munich. And his research concerned energy conversions and storage in the context of renewable energy technology. So I'm very actually happy to be here and honored to chair this session. The talk that I will try to be very short, but the talk is very interesting, and it's tackling the challenge of structural and compositional changes in the interfaces, playing a role in operating energy systems. So, Professor Carsten, please.
Thank you very much, Sylvia, for the introduction. Can you all hear me well?
I can hear you very well, yes.
Yeah,
Okay,
it's very
great.
nice. Thank you.
Good. Let me start sharing my screen. Okay, good. Can you see the slides now? Good.
Yes.
Okay.
Yes, that's perfect.
Good. All right. So as Sylvia has already introduced, what we're in my research, in my group, most interested in is what is nowadays very often called sustainable energy conversion. We need to really convert different forms of energy into one another all the time in order to eventually get a sustainable energy technology and provision for our society. Catalysis is playing a key role in this, of course, all forms of catalysis. And the problem that we have with this is, of course, the standard one. We're a little bit insatiable because we just don't have the right kind of catalysts. Whatever solutions we currently have in catalysis, you can very much helicopter type view, summarize them. Well, either the systems that we have, the materials, they don't have enough or insufficient efficiencies, they're not stable enough, or if we have something that works sort of like a decent, we can almost surely bet that it either contains a very rare or toxic material inside. And so we are in this continuous quest to always find better kinds of catalysts to eventually get to our goal. For a very long time, we thought that this is essentially a materials problem. So we just haven't found the right kind of material. And of course, it's very simple to come up with a Christmas wish list of the dream material, of its properties that we would like to have. Problem in general is that we don't really have a rational road of how we can get to this kind of dream material. So one possibility of how one can tackle this, if one then goes to modeling and simulation, is this simply computational screening. So we simply try out many materials and see whether one of these matches our Christmas wish list. The problem with that is that in the end, we now have realized that most of the problems that we have is not really actually a problem of the bulk material, but it is essentially more an interface quest. Because in our working devices, we typically have different kinds of materials and they need to work together in concert in order to give us a really useful device that we can work with. And it's exactly at the interfaces between different materials or interfaces between the different phases where all of the limitations and problems start. I've enumerated a few of these here. I'm quite sure that you know all of these kinds of keywords. Let me today particularly focus on one, which is this so-called working interfaces. Let me illustrate what is meant with working interfaces with the example of gas-solid heterogeneous catalysis. And you see here kind of a Mickey Mouse movie of a very simple catalytic reaction. It's supposed to mimic CO oxidation, and you see everything that I think you know from catalysis. I don't need to dwell much about it. The reactants arrive at the surface, reaction intermediates form, they diffuse, they react, and then they dissolve. And you see a lot of dynamics in this movie, which as a theoretician already makes me feel uneasy, because this is a lot of what we call rare event kind of dynamics, because it's still highly activated processes. But if you really take a closer look at this video, you see basically that the dynamics is almost essentially concentrated here in the upper half. And there's a very static part in that movie, and that is actually the lower half, and that's the actual catalyst material. Because in this kind of like generic view that we have of catalysis, somehow our catalysts are still quite static kind of entities. And there is now increasing evidence that sort of like challenges this established view that I think we all have in our minds, because this is somehow how we were all raised and educated in catalysis. These kind of new evidences, they come from all these emerging operando techniques that are now available in experiment, different spectroscopies, probe microscopies, but also, for example, electron microscopy. And let me show you here a classic example of this. It comes from the group of Robert Schlögl, also at our institute in Berlin. And you see here a copper nanoparticle on stream. Of course, we don't have atomic resolution here anymore, and it's a somewhat different time scale, of course, than my microscopic goofy video here. But if you look at this nanoparticle, this doesn't really look anything but static. It almost is reminiscent, maybe as if this guy is boiling and bubbling and it's in a liquid kind of state. And this kind of, and there's increasing experimental evidence that points in such a much more dynamic direction, in that really the interface is working. It's not remaining static. It's actually maybe the inherent dynamics of a continuous restructuring, new phases forming, that could be actually the key to a good catalyst. And this is not restricted only to gas surface catalysis. And we see it in all sorts of energy conversion devices. Of course, in batteries, it's inherent. We know this for a long time. This is the so-called solid electrolyte interface that forms between the electrode and the electrolyte. And also in electrocatalysis, if one really goes to technologically relevant current densities, we now see also strong changes of the electrodes that we're using. For example, here, this is Rutile kind of electrodes that work for PEM electrolysis. And in the end, if you really go to technological current densities, these things don't have any Rutile structure anymore, and they're wild guesses of what potentially could be the phases that form some sort of like hydroxides. Even worse, this sort of like restructuring is not something that simply just happens and eventually we run into a kind of steady state operation, because increasingly we use catalysis in a much more dynamic way, because we have to drive it initially with the renewable energies that are fluctuating. And so we're moving increasingly away from long-term steady state operation into very dynamic operation conditions. So these external conditions or changes in time are superimposed on maybe the intrinsic dynamics here, which of course makes the whole thing very complicated. And I think at the moment we are maybe just starting to see the top of the iceberg in what really could be happening. Of course, in terms of a modeling perspective, we are sort of like stuck then automatically with multi-scale modeling, because at the lower end, in the end, it is still reactive chemistry. And for this, we need quantum mechanics to get the bond breaking and making right. So our starting basis has to be electronic structure theory. We want to come up with a predictive quality kind of theory. But if in the end, everything is also maybe driven by macroscopic operation conditions, then we have to really go to macroscopic lengths and timescales, which of course then forces us to cover many orders of magnitude in time and in length. And over the last 20 years, an entire community has taken up this challenge of really doing such a multi-scale modeling in heterogeneous or catalysis or other forms of catalysis. It typically is a hierarchical multi-scale modeling approach. So we typically use different kinds of theories and then always give the outputs of a certain kind of theory as via handshaking as an input to the next kind of theory. Roughly at the moment, all existing approaches follow sort of like a similar strategy. Typically at the moment, one uses density functional theory for all the electronic structure description and the energetics of the elementary process level. And then one directly feeds this in some form of microkinetic model, a coarse-grained microkinetic model, very often, unfortunately, static lattice kind of models. And then one couples such a microkinetic description into a macroscopic continuum description, very often of heat and mass transport phenomena in a given reactor and geometry. And the problem at the moment, as I already briefly alluded, is very often that we're too static here on the level of the microkinetic models, and existing theories that we have and approaches, they just cannot cope well with these operando dynamic changes as we have seen, for example, in the movie from Robert Schlugel's department. And so today I wanted to just briefly touch on 2 points, showing a little bit where we recently are trying to contribute to this overall problem. And then the first one, just wanted to point out a little bit more this problem of these existing and prevalent static microkinetic models that are on the market. Now, the thing that I think you're almost all super well aware with is, of course, the way how computational screening is currently done in an approach that is very much connected to the name of Jens Norskov and all his co-workers. This typically works with quite simple mean field microkinetic models, and you assume certain reaction paths, and then you compute first principles, energetics for maybe few of these microscopic quantities that are really required, and you largely exploit so-called scaling or Bronsted-Evans-Polanyi relationships to get then all the rate constants that you need in your microkinetic model. One can discuss a lot of the approximations and assumptions that enter in here, but I think a much more fundamental problem or challenge in these kind of approaches is that in the end, one needs an active site model, a structural active site model for which we do the DFT calculations and set up our microkinetic model. And very often, of course, when we talk about an active site model in a coarse-grained way, we just write a star denoting it in a reaction equation. But if we really want to do a DFT calculation or so, we need to eventually write a structure file. And so then we need to really go to an atomistic picture. And this is not even a very complicated surface that I'm showing here, but the question is, by just looking at it, you can't really directly say, oh, this must be the active site that I use in my modeling. Traditionally, one had focused a lot on representative motives, in particular in work on transition metals. One typically focused on the 111 facet as being a more stable facet, and then simply took hollow sites, for example, or any other site of high symmetry at this terraces, and then some generic step sites in here. this could already lead to problems and limitations really for transition metals, but the problem is that in most of the energy conversion devices, we're now moving to much more complicated and complex materials, to compound materials, oxides, oxynitrides, and carbides. And their structural complexity is, of course, much stronger. And so the question is really, what kind of active site model are we using? Let me just illustrate this with a few examples of how tricky this actually can really be. This was work that we did with Rutile von Santen in Antwerp. The oxygen evolution reaction at cobalt oxide catalysts. And cutting a very long story short, in the end, it turned out that this is a calculated mean field microkinetic model with DFT data, that the most active site under potential bias that is relevant for this reaction, the most active site is actually a minority step site on a site or facet of these nanoparticles. And even more so, if we change the potential, it would be different sites that actually contribute or dominate the overall catalytic activity. And so if we had, in contrast, there's numerous computational screening studies out there on such kind of structured oxides that all, for example, use this generic terrace site down here, which is completely irrelevant in terms of its catalytic activity. And if you know this for this one example here, you question, of course, many of these results of these computational screening studies that try to find promising materials by maybe focusing on a completely wrong active site model. This is work that we did with Julia Kunze-Liebhäuser in Innsbruck. This is for CO electrooxidation in alkaline electrolyte. And quite surprisingly, whereas normally one uses platinum for this, they found in experiment that copper is really equally active, just at a lower overpotential down here, which is of course good news, because copper is a much more abundant material as compared to platinum. But then this was on 111 electrodes. If we try to really model this again in a microkinetic model, this would be the experimental current densities. This would be if we use the standard kind of microkinetic model that has been put forward for this reaction on platinum. This would be the theoretically calculated activity. And if we put this now to copper, we get essentially no activity whatsoever. And again, cutting a long story short, what really seems to happen is they did electrochemical STM. And once you really move to potentials where the reaction starts, you see a strong restructuring, a continuous restructuring of the surface. And what apparently seems to be happening is that there's a very famous reconstruction on copper that forms under these kinds of potentials, which has a lower mass density. So this necessarily leads to the ejection of copper atoms and small clusters onto the surface. And it seems to be these under-coordinated sites that really then drive the catalysis. And if we put this in a very simple generic toy model, such an atom, and then in the microkinetic model, we indeed recover exactly what has been seen in experiment, a very comparable high activity or current densities at a lower over potential. But it has nothing to do with a static copper 111 surface. And even worse, for example, if we can move to oxides, to now acidic conditions, OER, and on this rutile structured oxides, typically you see most of the screening studies focusing on the 110 facet of these rutile structured materials, because this is the facet that dominates the thermodynamic particle shape if you don't have any applied potential. But if you do ab initio thermodynamics and create a Wolf construction under applied potential, you see that really under relevant working potentials, at least thermodynamically, you would get a completely different particle shape that is now completely dominated by 111 facets. And if really, of course, in reality, we have to see how the kinetics limits us or what is really going on. But if you continuously have this thermodynamic driving force, it could actually be that all the computational screening has actually been done on a facet that might not even exist under operating conditions. So this was just a few examples to illustrate and exemplify a little bit how problematic and how complex the real situation could be. And if we just sort of like in a naive approach, use some sort of like generic active site models, high symmetry sites on some low index surface, we really could be completely missing So that would be a relatively negative talk. So let me try to show you a little bit why I think we can actually tackle this in the future. Problem, as I said, is that we have typically in this multi-scale modeling, we use handshaking, and we're very good in actually coarse graining and moving up in the scales. Of course, what would be needed is the way down, a feedback mechanism that tells us, depending on the operating conditions, actually what kind of structure we should be using. This is shown here a little bit more clearly and specifically for this structural aspect, that we actually would need a feedback loop that tells us which other structural model we should actually be considering. And we don't have that at the moment. But the minimum that we could try is, of course, rather than simply trying one active site, which is already expensive enough, very often if you do it directly with DFT, we could at least try to use many active site models. This way it's not really a direct inversion, but it would maybe give us a much better handle to tackle the structural complexity. And to show you why I think we are in a good way and shape to actually achieve this, as we can really go on at least to microkinetic models with many different active sites in there. Let me give you a brief timeline of how we actually proceed in our community with getting the right kind of energetic data, and namely the adsorption energies. If we use Bronsted-Evans-Polanyi relationships and scaling relations, the most critical input that we need from density functional theory are typically adsorption energies on these different active site models. And getting this started pretty much in the 90s when GGA functionals became available, and people computed, for example, an oxygen adsorption energy at a given high symmetry site on rhodium. They also computed it for OH, for example, another reaction intermediate. And I plot this in this graph where I show them really in this two-dimensional plot, and you will understand why I do that in 10 seconds. With increasing availability of codes and computational power, people did this also for other kinds of reaction intermediates, like for example, carbon and CH, and they did this for more and more kinds of materials, metals, alloys, for example, shown here. And if you plot this in these kinds of plots, all the different data that they have for different kinds of metals for these things, you suddenly see, and that was more or less the big achievement of Jens Norskov, that this roughly falls on a line. And this is what is nowadays known as scaling relations, which is good news, because if once we have established such a scaling relation, we want to do a new material. We don't have to compute, for example, both adsorption energies explicitly with DFT anymore, because it suffices to, for example, compute one with DFT, take the scaling relation, and then we get an approximate estimate of the other adsorption energy without ever having to do a DFT calculation. And of course, that reduces our computational demand, and we can do more complex models with more different active sites. So far, so good. The problem is, of course, that if you take a closer look at the absolute energy ranges that are typically shown in these kind of scaling relation plots, of course, yes, this all falls on a line, but you have these significant outliers here, and these can very often be, let's say, an electron volt away from the estimate from the scaling relation. And you all know that an electron volt or 100 kJ is everything in catalysis. It's basically between completely dead as a catalyst material or saving the world. And there's now, of course, increasing hope that we can actually do better than scaling relations and use machine learning to really get all of these adsorption energies much quicker through a machine learned model, including all of this scatter and really capturing these kind of outlines. And let me briefly show you our step on this. We worked on this together with Sergei Levchenko and Matthias Scheffler at the Fritz. And this is a compressed sensing ansatz, which essentially is called CISO. What it does is we want an estimate for an adsorption energy. And what we do is initially we set up a simple regression ansatz and simply say, oh, well, there's a targeted adsorption energy that we really want to learn of adsorbate J. Well, this must be somehow linearly related to some important properties of our clean catalyst surface. For example, it could be the center of the D band, the work function, site coordination, whatever we feel as physical chemists could be relevant in determining the adsorption energy. And if you just do really this linear regression ansatz, for example, you would recover the D band model if you take the center of the D band here as your candidate feature. So that would not be particularly new and thrilling, but what we now do is we can say, well, let's not just do this in a linear way, but let's introduce nonlinearity by also allowing mathematical operations between these candidate features that we believe could be governing our adsorption energy. So we allow them to multiply, to take exponentials, logs, roots, additions, subtractions, whatever. And this way, by combining now a set of features that we initially start with, in this way, we introduce a larger and larger feature space that we could test that in how it would predict our adsorption energies. And we're not even stopping there. We also say, well, why should this only be one such term? Let's also cover more of these kinds of things in here. And eventually you would be arguing, yeah, you must be kidding me, this is overfitting completely. And this is where one uses an L0 regularization to really only add, for example, such terms in here if they really make a meaningful and a statistically meaningful contribution to this. And so just to illustrate how this works, we use targeted sort of like a number of different reaction intermediates from syngas, and then trained this on a number of different transition metals. We used 2-1-1 facets so that we would have the terrace and step sites inside. And we came up with a list of primary features of what we in our group believe to be sort of like, and reading a lot of literature, could be relevant electronic structure and structural parameters that could govern the adsorption energy. You see them here, and I think that you're all quite familiar with them. You would have guessed similar ones. And then we computed loads of DFT data on the different kinds of adsorption sites. Here is a training set, around 350 DFT data, and then we train this CISO model. And what you see here is that it has two hyperparameters. So the descriptor dimension is basically how many of these terms in this sum here you actually allow or include. And the other one is the so-called rung. This is how often you have allowed for a mathematical operation in there. You see, for example, here on a rung 2 or 3 descriptor, you see that this already becomes relatively complex descriptions. But you see it also helps. If we start out here in the simplest one with simply one-dimensional model, this would be simply recovering the D-band model. We see that we reach a root mean square error that is significantly lower in around this kind of region. And what does this tell us now? And we validated this, of course, this root mean square error with another 500 adsorption energies that never entered into the learning. And this, we try to make it really actually a very hard test, because I'm initially not really much of a fan of machine learning, and so I wanted to actually see this algorithm fail. And we sort of like all the training data that we had used was only on pure metals, and then the validation data is for alloys. So the poor algorithm never had seen an alloy in his life, and I wanted to see how good could it predict adsorption energies on alloys. And you see that on average, the best kind of model that we found, it can actually predict adsorption energies with an error of about 0.2 electron volts. What does this mean? So if we want to, for example, now once we have trained this model with around 500 DFT or 340 DFT calculations, we want to do a new alloy that was never done before, we only have to do one DFT calculation of the clean surface of that alloy. That gives me all of the primary features that I need for my model, and then this model predicts me all adsorption energies on any high symmetry site on this surface, so terraces, kings, whatever, and for all of the different adsorption intermediates that we had included. So just one DFT calculation, and I get about 30-40 adsorption energies out for free for a new model. And so this, I think, illustrates quite nicely the power that these new machine learning models give us. And I think it's this reduction in computational demand of our, that originally we were up to now very often limited by the cost of DFT, that can really help us to shape up new microkinetic models that at least have many different active site motives inside. And that could be a very first tiny step to really trying to actively address this operando complexity of continuously maybe restructuring kinds of surfaces for really working kinds of Most of what I've discussed today has been published last year in this review in Nature Catalysis. If you want to read more about it, and don't let me stop without, of course, thanking the people that were behind all of this work. It's particularly these guys that were involved. So me, Albert, Hannes, Nico, Aubo, Daniel, Craig, and Christoph. I'm very grateful to them. I'm very grateful and thankful, of course, for our long-term collaborators on the experimental side and as well as on the theory side. Money comes from down here. That makes everything possible. And I thank all of these sources and these people, and I thank you for your attention.
Thank you very much for the very impressive talk. I'm sorry it ended. So I would actually listen more, but there are a lot of questions, of course. So I would give the floor to questions, and I'm sure people are converging towards questions. I will be even happy if there won't be any question, because there is more space for me to put questions, right? So I will enjoy the. May I? Are any questions at this moment? I don't see. Okay. I would. I enjoyed the talk very much. This is very well working on the same area, so it was really impressive to see how well the machine learning linked to modeling with molecular modeling can predict really properties of alloy. So that's really impressive result. Yeah, I would like to ask you a question, because when it's about the direct coupling, for instance, for coarse graining and moving up in the scale, there are also a lot of diagrams like this that include between DFT and microkinetical model molecular dynamics in the form of reactive force field, classical molecular dynamics. What is your view on that? Can this cover a bit of the direct coupling dynamics that is lost in the process between static process between DFT and microkinetic modeling?
Yeah, I think that is, I see a lot of potential there. I think it has been the problem in the past. Of course, the reason why we are so limited is exactly because we typically leave out the scale in between. So we directly jump from electronic structure to coarse-grained mesoscopic lattice kind of models. And this is, I think, the entire source of the problem, and makes us so much more limited as, for example, compared to the bio field, where they do similar kind of multi-scale modeling, but they first simply train or train a force field, and then they do all the molecular dynamics simulation, and then they do the coarse graining to the microkinetics. The reason I think why we, for example, and most people in the field have not really used this is that the classical force fields, the physical models that we have, they just were not good enough to describe the reactive chemistry. There are things like REACT-FF or other reactive force fields, COMP or so on the market, but I was never really impressed or convinced about their accuracy. So people have not used them. I think this is changing now, because again, we use or start to use machine learning. There is an increasing number of machine learned interatomic potentials that now appear on the market. For example, our group, we work heavily together with Gabor Chani and use these gap potentials, the Gaussian approximation potentials. And there, I think that, of course, the accuracy is never really the question. It's more the training. How do you do the learning? Because if you just learn enough, you can reach any kind of accuracy, but maybe the learning is so expensive that you can never get this to work. So the challenge there is to actually devise learning protocols that give you gap potentials with which you can work. And in particular, I think what we need to develop there, and we're working on that, is that we need to develop active learning protocols, in the sense, because if the surface is really restructuring so strongly and we initially have no clue about it, we might train a gap potential that can super well describe maybe a copper surface. But then eventually this turns into some copper hydroxide or something, and we would need new data. So if we anticipate all this in the first place, we need to come up with zillions of DFT calculations to train the gap potential to cover this entire chemical space. Well, if we have to do this, then it will break us our neck, because it, well, maybe eventually goes to some completely other region of chemical space. So I think what we need is to come up with active learning protocols that initially we start sort of like where we really think we start from our clean surface somehow, and then we let the microkinetic model run. It maybe indicates us that some restructuring will happen, and we have to retrain our gap potential to then describe that kind of chemistry well. Then we use it again to do dynamical simulations. Not something new happens. We, for example, in gap potentials, we could be exploiting the Bayesian uncertainty estimate or other uncertainty estimators to then say, oh, now I'm not so sure anymore. I'm extrapolating in a regime where I have no data. Then we request new data. We put queries for new DFT calculations in that range of chemical space, and then we retrain. And so that's, I think, where at least that's what is sort of like on the agenda of my group for the next 10 years, to develop such kind of active learning protocols, and then really come up with exactly what you are suggesting, really doing molecular dynamical simulations coupled and integrated with microkinetic models.
I promise to stay tuned on that, because I find it very interesting working actually. Energy materials, though it is, well, interfaces like you mentioned in the introductions are very important. So the interfaces between a hydrated and unhydrated is neither one nor the others. And this created a lot of problems that will actually be possible to tackle with the same kind of learning protocol actually. So very interested in that. But about the learning, there are any questions, by the way, please. I don't see, but maybe I have to activate to unmute somebody. I don't know. I think you can simply unmute yourself.
I see there's a question on chat.
On the chat. Oh, really? Okay. Oh, somebody cannot. Somebody is mentioning nicer deal on nonlinear transformations. Have you thought about using kernel regression?
Yeah. We're using it all the time in other areas. We started with CISO because it provides sort of like a super high efficiency. You really need very little data, and you can use this multi or parallel learning so that you really learn loads of different absorption energies at the same time. Kernel regression is better if you want to come up with a continuous, like a potential. Because CISO is a discrete technique, right? So you learn different high symmetry sites. And that also gives it its high efficiency in that you read only very little DFT data in order to predict loads of different absorption energies at loads of different high symmetry sites. We use kernel-rich regression actually quite extensively. It's basically also inside gap potentials, right? Because there's not really much difference between kernel-rich regression and the Bayesian Gaussian version. But we use it for continuous interatomic potentials. There we use it a lot. It's more efficient because then we can do molecular dynamic simulations. So CISO is really something that is only useful if you want just discrete absorption energies at different high symmetry sites. And there it's super efficient because it really only just focuses on this.
And for the training, yeah, the participant is thanking for the questions. Related to the learning process, the training data. If we refer to the example with the alloys that you mentioned, what is the computational cost in actually building a training data that will produce the accuracy that you showed with the validating data from alloy databases?
Well, let me show this here. So the training data, see, it's we use this 2-1-1 supercell model that is exactly shown here. And all in all, we did 344 absorption energy calculations. So it's basically 344 geometry optimizations. You put any of these adsorbates, oxygen on this side, you put it on here, here, on these different kinds of metals. So in total, it's 344 absorption energy calculations. I think nowadays for these kinds of slab models, one absorption energy calculation costs you an hour or two. A supercomputer depends on your parallelization. So that's roughly the cost. It's actually not large. It's negligible.
It's impressive. Yes, yes, yes. It's really very nice. Yes. Another question, is there any importance of the functional accuracies for adsorption energies for training data?
Well, the machine can never learn anything better than what you feed it with, right? So you will, if you train it with a certain DFT data, with one functional, so we used here B. van der Waals from the Norskov group. Well, in the end, our machine learning model can only predict me energetics that is sort of like consistent or compatible with this. It's garbage in, garbage out. If my energetics on the DFT level itself is crap, then my machine cannot make it any better. There are other ways. So there's a lot of this sort of like delta learning, it's called, where you, for example, learn sort of like corrections to higher level methods, for example. And then you do basic calculations with, for example, just some semi-empirical electronic structure method like type binding, Dft type binding or so. And then you just learn to extrapolate to maybe a couple cluster kind of level. That's a different way of doing it. But here, it's whatever functional we use for the training data, then that's the kind of energetics that we get on the machine learning level as well. And, so it's nothing has changed here. Machine learning cannot do anything to this respect. It's again us on the electronic structure theory side to hopefully choose the right kind of functional and have faith in that functional sort of like gives us the right kind of answer.
Another comment about DFTB is not leading then to the same direction with RSEF-GEFES, where you try to trigger some strings and fit something by, yeah. Yeah.
There's the nice thing is now that there are so many possibilities of what you can do. For example, in DFTB, I mean, what is the exchange correlation functional in DFT, which is voodoo, and the voodoo in DFTB is the repulsive potential that you use. And what people up to now use is some analytical expressions for this. Like in RSEF-GEFES, what you of course can do is you can also learn the repulsive potential. So that's one approach. You can use DFTB and then learn to extrapolate to, for example, couple cluster level in this kind of delta learning. There's zillions of avenues of how you can actually combine this. And this is, I think, how I actually view the prospects of all this machine learning. There's so much hype about it right now. And most of this, I think, actually, well, I'm unfortunately very often a person of direct words. So I think most of this is complete garbage, what is published right now. And because very often it's just people that think machine learning is cool, and then they come up with some solution. And once they have a solution, they find a pseudo problem that hopefully could be addressed with the solution that they have in the first place. And I think that doesn't lead us anywhere. I mean, in the end, we are people that work on catalysis and energy conversion, and I know my problem. So I don't need to find a pseudo problem, but I know my problems.
To be solved.
I think in the end, the big advantage is if we combine physical models with machine learning. I mean, why should I now forget 150, 200 years of research where we have understood a lot and just say, well, let's just learn everything again. So I know stuff and that I can use. Then other things we don't know yet. And for that additional, then I can use machine learning, because at the moment, apparently, we're not able to formulate this in a correct physical model. And then the machine can help me. But I think it's this hybrid approach that you combine this and also to fuse the machine learning into the multi-scale modeling methodology that we have. That's, I think, the way where we should go.
I like this message very much. I'm working on hybrid methods, so I'm fully agreeing on this and with the view on this. So yeah, it's great to have it to have your point of view. That also gives a very good feeling of confidence. In view of time, but if there are still questions, I will really take the opportunity of Professor Reuter being here and addressing more questions.
Is there still time for a question?
Yes, please. I will create that. I will take this. Okay. I will take this chance.
Okay, thank you. I actually also got a question actually on this slide. because you mentioned here you have some primary features where you thought would be important for the machine learning approach. Then in the end, when you have your, let's say when you have your trained your trained approach, then could you also say something back of which of these features were actually important in the training, or is it too much of a black box?
Yeah, that unfortunately is still the human input and intuition part, right? So this list of primary features we have to assemble. I typically use this image. This is where I get out my bottle of red wine, sit together with my students, and then we brainstorm and come up with stuff. If you then see, for example, these expressions that are found, there have been a lot of people, also Matthias Scheffler likes to try to interpret some physics into them. And I'm not super convinced there's much physics in there, because most of these primary features, they're not orthogonal, they're sort of like correlated to each other. And so very often what this algorithm tries to do is to come up with complicated mathematical expressions that fuddle these things together in trying to mimic maybe some other primary feature that we might not have in our list yet somehow. I've thought a lot about it. I don't really see much physics in there. What we see though is that there are certain primary features that recurrently appear over and over and over again. And that really is, of course, I think then telling us that these are really important descriptors in root or governing the absorption. And obviously, you see very often the D-band center. Obviously, that is the Norskov D-band model. We knew that. Actually, what was quite funny is that in this initial list, actually, I wasn't there, and my students were brainstorming without me, and then they had this first list, but they never really got to a good root mean square error in there. And then we sat together again, and then we brainstormed and said, hey, you don't have in your list anywhere the density of states at the Fermi level. Why don't you put that inside? And then my students looked at me and said, like, why should we include this? And I said, Jesus, you guys are so young. Have you never really read your Parr and Young book in the 1990s? This has to do with chemical hardness. Of course, this is all electronic structure theory, and maybe this is important. And so then we included this feature, and suddenly our root mean square error is basically halved. They were less than half. So it's good news if you find it, but in principle, conceptually, it's bad news, because it shows us how dependent this method is on us humans coming up with a significant list of candidate features. That, I think, is a big problem. That's also eventually why we're now starting to move away from CISO and rather do gap potentials or kernel-rich regression there, which is not as efficient. So we need more DFT data, but then we're not so much dependent on this initial list.
Okay, thanks. Thanks for the answer.
Thank you. It's important how not only our knowledge strong is, but our scientific intuition towards approaching world, right? So that's actually also playing a role in making choices of the right parameters. I would like to thank you very much for the excellent talk, and we promise to stay linked to the progress of this and stay tuned. Thank you very much.
A pleasure. Thank you very much.
Thank you. And next talk I would like to invite Wolfgang Schminker.
Okay, so I shall share the screen with you.
Yes, from the University of Ulm. We are very eager to hear about the storage of ions in nanostructures. And actually the unexpected results of how this ion plays inside and outside of a carbon nanotube is counterintuitive, I would say.
Yes, so this is a complete change of topic. I shall not try to solve the energy problems of the world, but I shall ask a very simple question. How does an intervening medium modify the interaction between particles? And in particular, can it transform Coulomb repulsion into an effective attraction? And the answer, of course, is yes, otherwise I would not give this talk, right? There's a well-known example, because we have the Cooper pairs which are known from superconductivity. And there we have an electron attraction, which is mediated by lattice deformation at very low temperatures. And we know that Sheldon Cooper got the Nobel Prize for this a couple of years ago. So what are the systems that we want to look at? We want to study the interaction between two ions, one inside and the other outside of a carbon tube. We have looked at two different carbon tubes. One is a semiconducting H0 tube. The other one is a conducting 5,5 tubes, and both of them are thin, and that means they're sufficiently small that we can do calculation by DFT. And these are the ion pairs which we have studied. Let me see if this pointer actually works. And as method, we have mainly used the DFT, but sometimes we wanted to look at very long tubes. And then it turned out that Dft Type Binding, which has been mentioned by Carsten Reuter also, works very, very well with these tubes. I'm going to show you something. So what happens is we simply started by putting an alkali atom or a halide ion into such a tube. And then if you then let DFT run, they then spontaneously form ions with unit charge. And the counter charge, which has then been transferred to the tube, this forms the image charge on the walls of the ring. And so these are the pictures that you get. You always have the charge ion. In this case, calculations were right for the center of the tube. And you can see the image charge, which is then close to the carbon atoms of the carbon tube. So this is the basic picture, but of course this is local, right? And it seems that practically you get the same kind of image charge formed, no matter if it is a conducting or if it is a semiconducting tube. And that means that the semiconducting tube must become locally conductive. And this one can see particularly well if you use the Dft type binding with a very, very long tube, which here in this case of the order 130 angstrom, right? And first, let us look at the density of states of the pure tube, which is this green curve. And you can see we have a band gap of more than 1 electron volt, right? And now if you put sodium atom inside the tube, for those carbon atoms that are very, very close to the sodium atom, you should see a very large shift of the density of states. Then the density of states, or the part of the conduction band, actually becomes partially filled, right? And this filling then forms the countercharge. And then if you go further and further on the position of the ion, the overlap with the Fermi level becomes smaller and smaller and smaller and smaller. Then the density of states becomes closer and closer to that of the pure tube. But notice that even for such a long tube, the presence of one single sodium ion leads to a sizable change in the work function of the overall tube. Somehow it just does not want to go on. Seems that
maybe just restart the slides and
yes, I think I'll go out of the
through.
Yeah. I shall stop this.
Yeah.
And out of the
the connection is also very.
Can you now see my screen? Yeah, maybe there's some connection.
Yeah, I think it's a problem with the connection indeed.
Okay, just a second. I go back to.
The screen is not shared yet.
But now it should be.
I personally don't. I still see you.
Yeah. Once again,
yes,
now we should.
I think it's starting.
Be able to see.
Yes.
Yes.
Yes. Well, it is a black screen, but it's a good start.
Okay, so we hope that it's a black screen.
Yes, there.
And now you should see as one slide stating we look at the interaction of two lithium ions.
Yes.
Okay,
yes,
fine.
good.
So this is the first system that we shall look at, interaction of two lithium plus ions. Oof. So these are the systems that we looked at. We have a carbon tube. We then first put one lithium ion inside the tube, let it find its optimum position and held it fixed at its optimum position. Then we place a second ion outside, change its position within the z direction, which is the direction parallel to the axis. And for each z, we then like to, we always then let it find its optimum position. And obviously, in this case, it likes to be above a hollow side. But then, as you force it to move along the direction of the axis, sometimes it has to follow over a bridge side, which is the second best side. Okay, so let's see what happens if we have one or two of these ions. Okay, the upper curve, the red points. These are the energy of absorption of the outside ion in the absence of an inside ion. And you can see these are the hollow sides and these are the bridge sides. We have periodic boundary conditions, so it goes bridge, hollow, 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 bridge, okay? What happens if we now place a lithium ion inside, and then we get this black curve, and you can see that in all positions, the energy of absorption is lower due to the presence of the inside ion by an order of magnitude of about 0.2 to 0.33 electron volt. And this looks like a virtual attraction between the inside and the outside ion. The attraction is somewhat weaker when the two ions are close to each other, and this is due to the fact that at this hollow side position there is still a very weak Coulomb field from the inside ion, which penetrates to the outside ion, and hence here at this position, then the effect is somewhat weaker. But this is a second order effect of the order of 0.1 electron volt. The question is what actually happens. And like I said, the direct Coulomb interaction between the two ions is weak and the field is almost zero. So the explanation must be sought in terms of the band structures of the carbon tubes and how they are modified due to the presence of the inside ion. So it is important that in this case, there's no chemical, there's no covalent binding between lithium and the carbon tubes. The band structure of the carbon tube is almost unchanged, but then the Fermi level is shifted so that the carbon tube, the piece that we look at with DFT, that this acquires a unit negative charge, and this causes a certain amount of energy, the shifting of the Fermi level. You can see the essence in this plot here. This is then the band structure, and for the pure tube, then the Fermi level is right at the center. And now we add the first ion outside, and then the Fermi level is raised, and it goes up, and there is a certain energy shift, and this costs a certain amount of energy. Then we add the second ion, and now the important point is the second shift is somewhat smaller because the density of states at these higher energies is higher. And that means that the energetic cost for adding the second ion is actually smaller, and these costs of the shifting of the Fermi level enter into the overall energies of absorption, and this basically explains what happens. Sorry, I think I have to, I don't know why I cannot go on. Sorry, I have to stop. Neue Freigabe. Bisschen freigeben.
Then you have to do the same as before.
It seems that every once in a while I have to.
Something is blocked. Yes.
Yeah, I don't know why it behaves so badly. Can you?
Now I can see you.
Now?
No, I can see you.
You should see a couple of the.
The connection is.
I think I always have to go back. I think that the connection is weak. I don't know why. Now you should be able to see it.
Yes. Now it's good.
Okay. Yes, it actually said that the internet connection is a bit weak. Okay, you can put this into mathematics, but I think I shall pass this by because you can see this later and you can study it in the paper if you want to. Once again, in a somewhat different plot, this is the changes or the shift of the density of states with respect to the Fermi level, right? Once again, this black curve here. This is in the absence of any ion. There's a comparatively large shift from here to here when you put the first lithium ion in, and there's a smaller shift if you put the second ion in, right? So when can this sort of apparent attraction happen? Well, there's a certain list which I've made here. I don't think I want to read this out because I've lost some time because of the technical problems, right? But I think it's obvious that these are conditions which must be fulfilled for this sort of effect to happen. And I think that can principally happen with carbon tubes. Somehow this behaves badly. Can you see it now? No.
Yes, I can see, but the old slides.
Yeah. But the difficulty is that I can't pass on to the next slide, and I don't really know why this happens. I think I have to reconnect. Sorry, but
don't worry. But maybe you.
Okay, go into presentation mode.
Yeah, maybe you show the slides like this. Maybe it works. Maybe it's something.
Maybe it is. Maybe it's simpler if I'm not in presentation mode, right?
Exactly. Yeah, I think so.
Right. Fine. Okay. Then I can simply pass on. Okay. So we go to the next couple, which is the chloride ion inside and the lithium ion outside, right? And first we look what happens to the density of states, but I should get rid of this stuff. I think at the moment you cannot see all of this, no? There's something at the right which...
we can see the figures. A bit of the text is cutted, but you can talk around. Yeah.
Okay. The most important point is chloride forms a partially covalent bond with the carbon tube, and that means that you see some new states coming up in the density of states of carbon if you have either an inside or if you have an outside chloride ion, right? So this means that due to a chemical interaction, there is an increase in the density of states of the carbon atoms close to the Fermi level. Obviously, since there is such a large change in the density of states of carbon, we cannot use the simple physical argument that we have used for the case of lithium, right? And this holds both for the conducting and for the semiconducting tube. Fine. These are the same kind of plots which are shown for the lithium case. Only in this case, the difference is these are the curves just for lithium outside, absorbing on the tube. And these are the curves which are in presence of a chloride ion inside. And you can see that there's a large enhancement of the energy of absorption of the outside lithium ion in both cases due to the presence of the inside ion. In this case, the explanation is simplest by looking at the change in the work function caused by the presence of the inside ion. And you can see for the A0 tube, it's 0.4. For the other, it's of the order of 0.7, right? The elementary process is you have a lithium atom coming from a certain distance. This then gets absorbed on the outside of the tube and gives off one energy, gives off one electron to the tube, and then it gains the work function. But if the work function has been lowered by the inside ion, obviously then the energy gain is somewhat larger. And this explains why you have this apparent attraction between lithium and chloride. Okay, so this perhaps is not so surprising, but now comes the last case, which is the interaction between Okay, the last case is now, I think you cannot see everything. Now it is better, right? This is the interaction between an inside and an outside chloride ion. And also in this case, there is a comparatively large effective attraction between these two negative ions, which is puzzling to us. And you can see that the effect is actually largest when the ions are as close as possible. Right, and this is the case of the A0 tube, but this also holds for the 5,5 tube. Now, obviously, this must be a purely chemical effect because the bonds with the carbon tubes and the chloride ions are partially covalent. You can see this in the density of states, but now there's a certain effect which you can only see if you go into the presentation mode. So, sorry, I have to go into the presentation mode, and it hope that this works. Okay, fine. This is the density of states in this case of a semiconducting tube, and you have a chloride ion inside, and as I've mentioned, there's a partially covalent bond which forms, and there's an increase of the density of states close to the Fermi level. No, it doesn't want to. Sorry.
Maybe in view of time, we go towards the last slide in order to.
Now you see something.
Okay.
Right?
No, actually, no. I will see you.
You see it?
We see you.
Sorry, no, I am not. I think this slide in this case is more interesting.
I think so, yes. I think it's working to visualize something, yes.
Yeah, but the difficulty is, right, and so this is the position. If you have one single chloride ion outside, and you can see there's a comparatively strong bonding, which you can see here. And now if this works, putting a second ion inside should shift these peaks towards energies which are lower so that the bonding becomes higher. It actually works, right? And you can see this peak has been shifted from here to here, which means that due to the inside ion, the chemical interaction of the outside ion has become stronger, and you can see the overlap of the peaks here, which indicate a partially covalent bonding. So there was one point which was a bit puzzling. The effect is strongest when the two ions are as close as possible. But this can be explained if you look at the density of states. When the two ions are close, there's actually a covalent bonding, in this case, between the two ions. You can see there's an overlap of the peaks of these two ions, which indicates a certain covalent bonding, which can only happen when the two ions are close to each other. When they are far, then the overlap is practically zero. There is no bonding between the two ions, and yeah, this only holds when separation is small. So in all the cases that we have looked at, there's always an apparent attraction between the particles. The explanation was somewhat different in the three cases. It is it is simplest. It's a simple physical effect. In the case of lithium. In the case of chloride lithium, the explanation was simplest in terms of the work function. And in the case of 2-chloride iron, this is a chemical effect. The most important point is that always the presence of the inside ion makes the density of states of the carbon tubes at the Fermi level higher, and this helps the absorption of the second ion. I think this is the essence of what you've seen. Finally, I would like to thank the audience, or audience because you're listening, yeah. And I would like to thank my co-workers. We have taken part, and this is a list of the papers which we have published on this topic. Okay, thank you.
Thank you very much, Professor Schnicker, for the interesting talk. Sorry that we encountered technical problems, but I think we all were able to listen. No, I think we went good. I think we missed some of the slides, but in big line we could follow. So we have to face also the challenge of the new times that we are living with everything online. So connections is one of it. So thank you. And I'm sure there are questions from the audience. Please feel free.
May I raise my hand?
Yes, please.
Can you hear me? Yes.
Yes.
I have a couple of more technical questions. So if I understood correctly, you first calculated the ions adsorbed or in connection with the carbon nanotubes in periodic boundary conditions, right?
Right.
How do you treat the counter charges for the ions?
The nice thing is this is one of the few cases where DFT works well with ions. Simply by putting a lithium atom into the tube, letting the DFT code run, the atom is automatically transformed into an ion. One electron is then transferred to the carbon tube, and this then forms the image charge automatically.
So you do not calculate the charge system, you put just the atom and you observe the charge transfer itself, and you see exactly one charge remaining on the lithium. And okay, nice.
Yeah, I'm also pleased that it happens, right? Because this does not usually happen with DFT, but this carbon.
Yeah, that's why I was I thought you put an additional charge. Okay, now I understand also the shift of the Fermi level. And the second question, also very short. The results you showed on the lithium, they were also obtained by DFTB, or these were pure DFT?
The energetics, they were all based on DFT. Only when I showed the long range or the long range effects, right? How the density of states changes with the distance from the inside ion. These were done by Dft Type Binding.
So, because which parameters, which Slakophiles you used for the DFTB calculation? Because to my knowledge, there is none for lithium carbon.
Yes, I think you are absolutely right, and I think I cheated a bit because what I actually showed was for a sodium ion, but I think I mentioned. Yeah, exactly. I think I mentioned that this is a sodium ion. We have parameters for lithium, but they don't seem to work well. Sodium works perfectly.
Okay, so which set did you use for the sodium?
This is a standard set, right? I forgot.
The 3OB. 3OB. Okay, great. Yeah, nice, thank you.
Mm-hmm.
Other questions? I'm happy that was the question about parameterization of DFTB. I had the same, but it's also interesting to see the side effect of the carbon nanotube are actually not playing a significant role. So it's actually.
Yeah, but like mentioned, even for such a long tube, you still see a sizable shift in the work function, right? Or
exactly.
position.
Yes.
And
yes.
Yeah, but of course, even for a carbon tube of this length, this this corresponds to a concentration of sodium ion of about 10 to the -3, which for a semiconductor would be a sizable doping, right? So
yeah, right.
A shift of the Fermi level. But we can make this longer. Only then we have to be even more patient.
Yes, exactly. Yes. Thank you very much for the nice talk. And in view of time, we have to move further. But I'm sure that maybe there are extra questions. Please put them on the chat. Thank you, Professor Schmickler. We have to.
Welcome.
Yes, thank you. We will move to the next talk. Please feel free to use the chat. It's working perfectly. I would like to introduce the next speaker, and I hope, yeah, Aneta is here, available.
Yes, here we are.
Yes, okay. Hello, hi. I hope that I pronounced the name correctly. Aneta.
And Jarek.
No.
Jarek is okay.
Jarek, okay.
Jarek.
From University of Wrocław, Poland. And yes, please, you have the floor.
Okay, so hello everybody, greetings from Poland. So before we start, first of all, we would like to thank to the organizers for an opportunity to present our results. And we would like to thank to Professor Bartłomiej Szyja for inviting us. And our presentation, we would like to say maybe a few words about proton dynamics in hydrogen bonded systems. For today, we choose so-called proton sponges.
And now let's start the presentation. We will put it into the presentation mode. Share screen.
And we will start.
Okay. Okay. Can you see our presentation?
Yes, yes.
Let's hope so.
No. I can see you, but I cannot see the presentation.
So let me try once more to share screen. Proton sponges share.
Yes, now it's okay.
Okay.
Now it's okay. So the presentation view. And let's try. So proton sponges are a class of compounds known since 1968. And their main property is simply that they catch protons whenever they can. It doesn't mean it goes fast. The kinetics of this can be slow, but the equilibrium constant is shifted very much to the proton being shared between two nitrogen atoms. You cannot see the proton here exactly, so this is the proton sponge before it catches the proton. The acidity constant, as chemists like to show, is very low because it is a minus logarithm. So the basicity constant is, on the other hand, very high. So proton sponges are one of the most strong organic bases. We will show some results on the proton dynamics inside the sponge because we think it could be at some point used as a memory material or maybe signaling pathway in nanoelectronics. So this is a prototypic compound, DMAN. We will have also a slightly larger system. We will compare the dynamics between the two of them. We will do it in the light of Karp-Marinello molecular dynamics, DFT based with a well-known PBE functional. So this part of the talk will consist of two parts, is divided in, will show the gas phase results. So this is these are the gas phase results for the proton inside this compound and this with much larger substituents. And you will see that the dynamical effects are not as connected with the change of substituents, but simply with the sheer size that these substituents are large and heavy. But I am going ahead. So let's see that our setup is quite conventional, norm-conserving pseudopotentials, a cutoff, a standard value for electronic fictitious mass, a time step rather conservative to observe the proton dynamics very accurately. And in order to see the dynamics as a chemist could see in a test tube, okay, not test tube, we are showing you the gas phase results, we use the room temperature. So first we equilibrate and then we release the molecule from the thermostat so that the dynamics is not anymore constrained by thermostats. And you will see that 20 picoseconds, which was already quite demanding for Carparinello, is enough to see the essentials of the dynamics. So the metric parameters that we chemists associate with hydrogen bonding are, first of all, a donor acceptor, that is nitrogen-nitrogen distance. Of course, you can imagine that these compounds look symmetrically. If not for the proton, you could have here a symmetry plane, which means that the assignation donor and acceptor of the proton are simply a matter of choosing the starting structure, which of the nitrogen atoms caught the proton first, the left one or the right one. Then, of course, donor proton and proton acceptor distance. And you will see that the proton is shared between two of them. We don't put here the numerical value, but 49% of proton possession, but one of them, 51 by the other. So, of course, it is not 50-50 exactly because of a not yet fully converged statistical sampling by Carparinello MD. So if we ran this several months of wall time longer, we would have 50-50%. But it is 24 picoseconds here, it is 24 picoseconds here, and you can see even graphically the large difference in the dynamics style. What happens here? In the lighter, smaller proton sponge, the proton simply moves back and forth between the donor and acceptor. But in the other one, it stays at one point, goes to the other side, changes. So these periods of residence are longer. What does it change in the structural parameters? Not too much, because when we calculate the average values of structural parameters, we see that the larger proton sponge has slightly shorter hydrogen bridge distance, which means in chemical terms it should be stronger, so it is. And here you can see a not perfect equalization of the distances. They should be, in principle, the same if the proton is shared equally, but they didn't equalize yet. Now, what we like is observation of vibrational properties. Vibrational properties reproduced from the Carparinello dynamics can be obtained in two ways. First, autocorrelation function of dipole moment would be something, using, of course, quantum correction factors, would be something that experimentalists see as an infrared vibrational spectrum. But the drawback of this is that you see the spectrum of the whole compound, the whole molecule producing the dipole moment, which means that you cannot see where the proton is, what is its vibrational signature. Of course, you can suspect that here positions at strange wave numbers, strange for infrared spectroscopists, mean that hydrogen bond is here. But we can also do the transformation of the atomic velocity power spectra, which means we lose correct experimental intensities, but we get motion intensities, which means we see at which wave number the proton is oscillating. Since Carparinello is a classical nuclear dynamics, it is Newtonian dynamics for nuclei, but DFT for electrons, of course, then you don't see one oscillator. Many things are coupled, but we like it because we can observe changes of the vibrations of the vibrational scale when the heavy atoms are moving back and forth. So strangely, for the lighter proton sponge, we have a very nice definite signal at 1500 wave numbers, which is very redshifted. You would expect hydrogen signals at 3000 something reciprocal centimeters. So it is so much shifted back by the anharmonicity, by the very soft, almost single well potential. But what happens for the other system? Here you can see that the proton had enough time to develop several types of dynamics. Almost free proton when it resides close to the donor or the acceptor, and the proton being shared, which is even much redshifted than here. Unfortunately, both of these cases experimentally give rise to such strong absorptions that you cannot really distinguish it experimentally. The free energy surfaces reproduced show you a very classical example. So when you shorten the distance between the donor and acceptor, you are forcing the proton to be shared. But we introduced here the minima, and you can see that in fact the potential is not single well with barrierless transition. There still remains a very small classical barrier. It would be swallowed in nuclear zero-point motion, but in classical CPMD nuclear dynamics, it is present. For the larger system, where the sheer mass of the substituents makes the dynamics much more diverse, first of all, the position of the minima are at larger proton shifts from the equal position, and here also the barrier increased. So here it is strange, but the proton has larger barrier than here. So that was the first part of our study, in which we showed that two time scales of dynamics can be observed computationally in these two molecules. In DMAN, the dynamics is so fast that the proton is able to develop only one vibrational feature. But for this one, you can see two regions with distinct vibrational behavior. And now let's move to something not totally different. It is also proton sponge, but it is so strong that it swallows its own proton. The idea of the experimentalist Stab, Krieger, and co-workers in 1997 was to develop a compound with two hydroxylic groups, OH here, and empty here. But it swallows the proton of one of these OH groups, it moves here, and it forms a Zwitter ion. So here, the structure of the compound in its zwitterionic phase was measured crystallographically, and we were able to calculate the CPMD dynamics with more or less the same setup as you saw, using not only gas phase, but also crystalline phase. For this, we also included the Grimme D2 corrections to see whether they make any difference in the gas phase and in the solid state. So what is the question we are looking at now? Do these two protons, upper and lower, move in sequence or not? Are their movements independent or maybe dependent? Or if they are dependent, do they like to be on the one side of the molecule or on the opposite sides of the molecule? So which means if that one goes right, that one also wants to go right, or if one goes left, the other goes right. Let's try and see. Well, from this type of dynamics, we cannot see, we cannot answer the question. The dynamics is not different between the gas phase and the gas phase with dispersion corrections included, neither in that one or in the oxygen-bearing bridge. The same for the crystalline phase. Whether we include dispersion or not, it is the same. For computational reasons here is only 14 picoseconds dynamics, here is 28, which means that you should compress in your eyes this right graph, and then of course it would resemble you that one. So we cannot answer the question what is the relative position of the upper and lower proton. If we look at particular snapshots of the dynamics, I don't know if the green line is visible because it is very thin. I hope it is. We observe many different cases. For example, one of the proton is moving and the other follows. One of them, or they behave totally independently, which means that just looking at the distances and even at the time evolution of the distances doesn't help. Spectroscopic analysis shows you that the dynamics in gas phase and in the crystalline phase are slightly different. In the gas phase, there is more freedom and the vibrational features are more smeared out, which means that simply the molecule is more free, doesn't have neighbors, and the heavy atoms can move more and introduce more anharmonicity to the proton potential. In the crystalline phase, everything is well defined. You have very nice proton position because the heavy atoms, this dynamics of the heavy atoms is simply governed by the neighbors and the crystal environment. So let's return quickly to the question of the relative position of the two protons. When you calculate one-dimensional free energy profiles for the one bridge and the second bridge, you see how low the barrier is. So effectively, if you would include 0-point corrections, there should be no barrier. And again, the one-dimensional free energy profiles don't show you any correlations. Here, what you see that it doesn't go to zero, the wells are not equal, but they should be. It is again the result of statistical sampling. When you move to two-dimensional free energy surfaces, first of all, you see what you saw before, that compression of the donor acceptor distance, which means going lower here, makes the atoms, the hydrogen atom more equalized between the donor and acceptor, being placed in the middle. And still only in the crystalline phase with dispersion, we see any noticeable changes in the potential energy surfaces, which is in fact to be expected because, of course, in one molecule, the dispersion correction would maybe add some almost constant shift to the potential energy surface and nothing happens. But in the crystalline phase, it is, after all, the dispersion and, of course, hydrogen bonds between the neighboring molecules, which holds together molecular crystals. And now one of the last slides, two-dimensional free energy surfaces. Here you find the answer. On this axis, you have the proton transfer coordinate, which means does it like to be in the middle, on the left, on the right, for one of the bridges and for the second of the bridges. And when you indicate the minima, you can see that the protons tend to be on the opposite sides. I hope that going back several slides doesn't introduce any lag to the presentation. So that is the preferred situation, the one on the right. You could explain it on the basis of simple electrostatics, which means that if you have that situation, so then the contact between the formal plus and formal minus center is the best and the transmission is through aromatic system. Here the path from plus to minus is larger. So that one is slightly preferred, but very slightly, since you can see the energy scale, it is just 2-3 kilocalories per mole. So now we are happy to show that Carparinello MD on proton sponges can show you what happens to the proton, that its life is not just being caught and held, but it is possible to develop different time scales of the dynamics and also to try and introduce correlation between proton motions, which hopefully can be used in the future, for example, for some kind of signal transmission in molecular electronics. And here, let us finish with thanking our National Science Center for supporting this work. and of course our supercomputing centers, because you know as well as we do how costly the first principle molecular dynamics is. And of course, we would like to thank you for your attention, and we'll be happy to answer your questions.
Thank you very much. Yes, we all know indeed. It is a question indeed. We'll start with a question on chat. Do you think enabling a solvation model will influence the proton position in the sweeter ions?
It could be well, because exactly at the first approximation, you could think of a crystalline environment as a kind of introduction of dielectric function, dielectric constant, which would be exactly some kind of PCM, some kind of solvation model. But of course static, because you know where the neighbors are. So definitely it could be done. The problem only is that after some equilibration, the environments of the solvent would be also isotropic. So if you would like to do something with this, you in the solution which would be isotropic, it would be necessary somehow to introduce, I believe, some kind of symmetry breaking, maybe by substituents of the proton sponge, which in fact is what we are doing, but we didn't show these results. But let's say proton sponges with broken molecular symmetry, not electronic, but simply with introduction of specific substituents at only one side of the molecule, is exactly under our interest now. So thank you. Exactly, we are trying to move the proton using chemical substitution, because quite probably we didn't calculate the PCM, but rather it should be isotropic. On the other hand, you could calculate in calculations, put electrostatic vector in any place you wish. So it is also an option.
Thank you very much. There are very interesting results, very interesting presentations. There are a lot of questions on chat. In due of time, we have to move forward. But I leave the space, chatting space, for exchanging more ideas. Thanks a lot. And we will move forward. Our next presenter is coming from Instituto de Física Fundamental Madrid, well, where the conference was supposed to be. Should show us around Madrid, right, at this moment?
Yes, yes.
Now.
Should I start the screen now, may I?
Professor Campos Martinez, yes, I can see you.
Yes, I am sharing the screen now.
At the moment.
Sorry.
Don't worry.
I am first putting the screen. I am sharing the screen now.
It's okay. I'm the guilty one today. Okay. I take all the blame on me with all delays. So everybody, please be relaxed.
This one now?
I will try to. Yes, we can see it.
Okay, thank you. So hello everybody. First of all, congratulations to the organizer for the excellent work in the organization of this conference, and also for inviting me to present our work that has the title Separation of Helium-3, Helium-4 Isotope by Nanoporous Graphene, a work that has been done by Massimiliano Bartolomei, Marta Hernández, and José Campos Martínez from the Instituto de Física Fundamental, CSIC, and also by César Moreno from the Catalan Institute of Nanoscience and Nanotechnology, and Aitor Mugarza for the ICN22 and ICREA. So very sorry. Oh, it's not. I have, now. Okay, so a brief outline of the talk will include the introduction about 2D material. It's very well known for everybody, system and goals. Then we will move to the interaction potential. That is a very important part. And then we'll further discuss a little bit about dynamical calculation and some discussions and conclusion. So for the introduction of 2D materials, this is a non-exhaustive list of all the applications that people know about two-dimensional material. We are especially interested in this part, is the use of this two-dimensional material for the separation of gases, and in particular for isotopic separation. You can see here that the families of the two-dimensional material is very large, including graphene and many others. So this is like a list of the number of papers published in this field, that you see that there is a tremendous and increasing rates of publications. And below you can see here some of the recent reviews, if someone is interested. Some of them are for the system that we are working more of it, and some very recent for this year. So instead of using this kind of system like graphene, we are using a new kind of material, nanoporous graphene, that is a new material that has been recently synthesized by the group of Aitor Mugarza in a bottom-up approach, in which they were able to synthesize a material, a two-layer material that has pores very well designed, a very specific position, very regular position, with the very same site and same position for all the material. This is in contrast with the previous material, most of them which has pores of different size and also was placed very randomly. So our goals in this talk would be the accurate, in principle, determination of molecular layer interaction and global potentials for the atoms and molecules with the two-layer materials, and how the quantum mechanical effect will affect to the absorption of molecules or the transmission through the nanoporous membrane that can be applied to filtering, storage, and different kind of things. And in particular, in this case, we will discuss about the helium passage through carefully tailored nanothallium materials, and this if the isotope of different mass can affect the separation of this species, but it's called also the quantum saving. Okay, for the interaction potentials, we don't use the new modern technologies in which nuclei and electrons are treated at the same level, but we instead use the Bohr-Oppenheimer separation, that is to say, to the concept of potential energy surface, in which the nuclei are kept, are kept in fixed position, and then the energy of the electron are computed. Once we have the electronic energy compute, we have a potential energy surface in which the nuclei move, and then we can fit this potential energy surface to a functional form that, in our case, you know the Lennard-Jones potential is a very well-known fit for interaction potentials that include only two parameters. One of them is the well depth here and the equilibrium distance. Instead of this simple formula, we use a little bit more elaborated ones, that the authors call it the improved Lennard-Jones or modified Lennard-Jones. That is a version of this Lennard-Jones potential that include one more parameter, but in turn allow you to have a more flexible fit of the electronic energy to the analytical form. This analytical form is based on some correlation formula between some molecular properties such as polarizability, but in our case, what we do is just we first use these molecular properties to guess an initial parameters, and then we use a very high level of initial calculation. In this case, that we will show here will be the DFT with this functional and with this basis, and then refit and retune this calculation. So to see how we proceed, we will begin here with a case of the graphene that is a simple and very well-known case. The graphene is, everybody knows, a carbon allotrope composed of sp2 carbon atoms. So here in the graphene that we have the layers, we first identify a suitable molecule or model in which we can perform the calculation, that high level of initial calculation. In this case, it's very simple, is the coronin. So with this molecule, we can have this calculation and see how is the interaction between the atoms and molecule approaching the coronin. So in the case of the nanoporous graphene, it's a little bit more complicated. We don't see here any more typical like coronin molecules. So we have also identified a prototype here that the first thing is that we have used it like a molecule. You allow me to call this prototype or molecule, and then we have make sure that this is a stable molecule. We'll let this prototype to relax to the minimum, and with this prototype on molecule, we can just compute the interaction. So the general procedure would be to use just a brief version, to use molecular properties, polarizability, or other molecular properties, and then use affinity level theory to compute the same interaction, and then reevaluate these parameters with the, and then finally to some overall interactive system to get the global potential that is our goal. So how this works in the case of graphene, that is the first case I showed, that is the easy one. You see here a chlorine molecule, here is the helium, and this is the approach of the helium to the chlorine molecule in 3 typical positions, the bridge, top, and hollow. And you can see here how is the agreement between the ab initio points here in these dots, these points, with the continuous line that is the fit to this formula. You can see that the agreement is very good, a little bit worse for the case of the hollow. And in the case that you have a heavier atom, like the argon, you can see here that the agreement is much better. So this is the case when we have the isolated molecule. So how this performs when we move to the layer. This is a case when we can zoom up over all the layer of all the surface, and we can have the global interaction potential for helium and graphene. But also we can use the several layers of graphene to have graphite. And in the case of graphite, we have experimental results for the first and second and third, but we are just looking here at the first physics state, and the result that we can get computing the bound state on graphite, that you can see that compare well with the experimental results. So we think that the method worked quite well. And this is the result for the nanoporous graphene. Here we don't have experimental results to compare with. So this is just a comparison of how the high level ab initio calculations here in dots and squares, small ones, and the fit works in the when we approach perpendicular to the molecule, and when we move in the C and X direction, so that is to say in the surface, the molecule. This is the case in which we have the isolated molecule, the isolated pore that we will be developing. And in the case that we put a helium in the middle, the structure relaxes, and we have another slightly different geometry. So in this case, we can also fit how is the potential formula that we have shown before, and you can see here the agreement in this the ab initio calculation and how the fit is, and this is also about the X and Y direction. So this is isolated pore, and this is a pore with a helium in the middle. So for the dynamical calculations, what we have here is that we will have 3 steps in carrying out the dynamic calculation. First of all, we will move from the prototype to construct a unique cell and the 2-dimensional layer, and then we will solve the time-dependent Schrödinger equation, and we'll extract then the transition probabilities and rates. Okay, so this is the isolated pore we get when we, to the prototype of the molecule, remove the atoms that are redundant, and we have to add some of them. And this is the hole, the pore that will appear in the nanoporous graphene when we construct with the lattice vector and add with the layer. This is the layer in which we are going to see how is the transmission of isotopes. In the case that we use the geometry, the structure in which they have been optimized with the helium in the middle of the center of the pore, this is slightly different, but there is not much different. The only thing is that we have a layer at the end that is slightly, but only a little bit more slightly corrugated than the first one, but there is not too much difference. But the difference can be seen much better here when we plot how is the interaction potential when we approach the helium atom. Here you can see the potential interaction when we have the 2 cases when the pore has been isolated, has been optimized in isolated, and with the pore has been optimized with the helium in between. You can see that the potential energy as we approach is the same, except when you are very close to the pore, when the interaction is almost half of it. So this is the situation. This is the kind of structure we have used to construct the nanoporous graphene and to carry out the calculation. So the effect we want to study are the quantum effects that mainly are the 2 kinds. One of them is the tunneling that favors the lighter species, the helium-3. And this is the barrier that has to surmount the atom to pass through the membrane. And the other one is something that is very well known also, is the 0-point energy of the levels that you can find here in the pores. There are some quasi-bound state here in the direction of the surface. So in this case, however, the species that are favored are the heavier one, because the bound state is closer to the bottom of the well. So what we see here is that there are opposite effects in that the tunneling favors the lighter species, while the 0-point energy favors the heavier species. So to compute the transition probability, we just propagate a two-dimensional wave packet and then fully transform the wave packets to get the stationary wave function. And with this, we get the flux through a surface here. And then from there, we can compute the thermal rate constant that includes some Boltzmann factor, and this that is the translational partition function. We can also compute the something that is much better known, that is the permeance in this context, that for transmission and for flux through membrane, they include also the transmission probability here that has thermal average, and you have here the permeance with this formula. So these are finally the results. For transmission probability, the helium-3 in red and helium-4 in blue. There are several features that are worth to comment. The first one is a typical ladder figure that corresponds to the different quasi-bound state that you can find here along the surface. This is very peculiar due to this 0-point energy and the others upper states in this pore. There is also, you can see here that this is a closed loop here to a lower energy, that the lighter isotope has a much larger probability, and then is crossed at some point by the blue, that is the heavier species, that is the bottom on the top. So also you can see here that the threshold is a bit earlier in energy for the heavier species, and then there is a plateau in which the lighter species, the helium-3, has a slightly more probability of transmission through the membrane. This is due to the fact that because you remember the lighter species has the bound state that is a little bit higher in energy, so the wave function is a little bit more spread than the heavier species, so have a little bit more probability. With this, we can compute the transmission rate coefficients, and then you see that there are small numbers, so there is not too much difference. You can see only that there is a higher difference here as a very low temperature, and then you can just have this relation between the rate for the heavier and the lighter species. And you can see that this relation has a maximum about 25 Kelvin. That would be the best selectivity for this kind of membrane. And the number is 2.5. So in the literature, it's appeared that 6 is the number that you should get for being industrially or technologically relevant or feasible. But still, we can see here that the fluxes are very good. So in the case that we compute another material that has been used for this kind of property, the separation of isotope, that is graphite. You can see here that is similar, not so, it doesn't increase so quickly to a high value, and that the values are much smaller. So you can see that the nanoporous graphene is at least 4 orders of magnitude more flux than the previous graphene that has been other membrane proposed for separation of isotopes. So if we move to permeance, you can see here that the permeance also has similar figures. The nanoporous graphene increases very quickly and is much larger than the previous material like the graphene. And this line here is this is units of permeance. Permeance unit. This is a value of 20 GPUs, and this is the value that is generally accepted as the one after which you can have good permeance to be used in industry. So you can see that at very low temperature, you can have that this material is already able to have a larger flux. And this is the graphene, and also here the comparison of selectivity, that is the same that you can get with the rate constant, as it cannot be otherwise. So to finish, I would like to say that we have performed three-dimensional quantum mechanical calculation, the transmission of helium membrane, so the quantum sieving of helium isotope, that the quantum effects, tunneling and 0-point energy, also resonant, that we haven't spoken about here, are very important. And to see that the quantum sieving is still a big challenge because the selectivity is still low, but we think we can tailor the membrane to get a better selectivity. And also, but however, in this case, the fluxes are much larger than the previous material, and the possibilities are many in this new material. So the real challenge is to achieve both high selectivity and high flux through the separating membrane. And nanoporous graphene offers a unique opportunity for it. And with this, thank you for your attention.
Thank you very much, Professor Martinez, for the interesting results. We have time for short questions. Well, there are definitely come in the chat. I have one about internal cooking, actually, because at a certain moment you are showing how these potential were derived. So as I understood it correctly, going from parameterizing the polarizability in beta parameters from DFT and then passing on Lennard-Jones type of potential.
Yes.
And then actually go hollow and the top and doing the summation of this potential.
Yes.
Summation or mean would have, was it a choice there, or does it affect actually? Okay,
so we assume that because these are weak interactions, this is the first thing, we can use the pair interaction potential. So you sum up of other atoms. That was the idea, to show the effect when you sum up over all the layer in graphene that we have. Well, in graphite, we have experimental result. We only have to compare with experiment. And then you can see that the agreement is quite good with regards to the bound state that they are measuring, actually. Yeah, there are also many others theoretical results to compare, but I think the experimental are good. And the only thing is that, of course, the comparison with experiments is made with graphite that is only made of several layers of graphene. It's not that there is no actual interaction between. So it's, for graphite, let's say that our surface is less correlated than the actual one. Okay, but for a single two-dimensional layer, we don't have experiments to compare. So
I get, yes.
For other theoretical results, is in quite agreement. This formula gives, and it's a global potential. You can use it for molecular dynamics, for quantum dynamics, for everything. So it's not.
Yes. Any short questions? Then please keep an eye on the chat. They are going probably to come. We proceed further. Thank you very much.
I want to meet.
Thank you. Our next presenter is coming from a combination of institutes and technical university, coming from Brazil to Germany. Florian Günther.
So you can see the screen already? Yeah.
Yes, we can see you and we can see the screen. Yes. Perfect. Please, Florian, have the floor.
Okay, so thank you and welcome everyone. In my talk, I would like to present you some of the results that I obtained during the past 6 to 7 years, mostly during my PhD work, where I was working on so-called donor acceptor polymers. And since this, from my knowledge, is the first time that we are talking about this material type in this mini-colloquium, I would like to start with a short motivation why we are interested in this material. And I think all of you will agree that in the past years, electronics have become a very eminent part of our daily life. This conference is only possible due to technologies nowadays. And it puts us in the situation that we have certain expectations about the future. What we expect, where devices can be evolved more in our daily life. And to obtain those devices, the inorganic semiconductors might not be enough anymore because we need more functionalities that cannot be obtained. For instance, flexibility, lightweight, transparency, also biocompatibility if we want to include them also in the body. And for this, we need other materials. And organic semiconductors are one kind of this that already find some applications, for instance, in the forms of organic LEDs that are typically in the displays of our smartphones. And a subgroup of this organic materials are semiconducting or conducting polymers, the research of which got particularly boosted by the Nobel Prize in Chemistry of 2000 for these three guys who did the early works on that. And the key property of those polymers is this so-called conjugated backbone, which means an alternating sequence in double and single bonds. And the advantage of this material is that it can be processed from solution via printing techniques and therefore create to fabricate very cheap devices on flexible substrate and also in a large scale. However, we are still far away to really know everything what's happening in this kind of material type, and we are not able to say which is the best material to use for certain application. So we still need a deeper understanding to be able to do such predictions. And this, of course, depends what you're investigating, but in my research is mostly about the electronic properties. So for instance, the conductivity. The conductivity, you know, can be easily expressed as the product of the electronic charge, the charge carrier density, so the number of charge carriers we have in our system, and the mobility, which is something like the velocity of those charge carriers in the system. And this first generation of semiconducting polymers, so that only consists of this conjugated backbone, had very, very low mobilities if we compare this to silica. And over the years, there were so chemists applied some functionalized those materials, and it arises what we call the second generation, what I call second generation, with some heteroatoms and some solubilizing side chains that were able to increase this mobility a lot. And when I was starting my PhD, it was in 2013, a new kind of, a new class, a new generation of the semiconducting polymers occurred, which are these so-called donor acceptor polymers, in which one combines electron deficient and electron rich units to design special properties and increase those electronic properties. And with this kind of material, it was able to obtain mobilities that were again 2 orders of magnitude higher. And this material, this decatopyrrolo-pyrrole unit, over the past years became something like the new workhorse of this type of research, which before was this P3HT unit. So nowadays, when people are trying to look for new device architectures and stuff, they are typically obtained with materials like this. So it followed me through my whole research since then. And I have worked a lot, so mostly theoretical, which is all of these blue boxes. So starting from, of course, simple geometry and electronic structure investigations, the charge transfer, molecular doping, conductance with internal regime, and what we are also interested in are the defects, what localization defects may induce in those systems. And after my PhD, when I came to Brazil, I also started to work experimentally on those systems. So I'm now also doing some synthesis of them and device fabrication. For the talk today, I would like to give you an overview of these 3 topics, and I would like to start with the charge transfer. In this picture here in the middle, you see how when you have deposited film on a substrate, how these polymers may align. They typically align in this parallel orientation. And here you may think about 2 different transport directions. One is along the chain and one is perpendicular to it. And if you think about a single polymer, will never be able to, in this large scale devices, to connect both of the electrodes. What we need to have a transport through a whole system is this transfer between parallel chains, how it's depicted in here. And how to calculate this transport? For this, there can be used the so-called Markov transfer theory, which gives us an equation to estimate this transition rates, so how a charge may hop from one chain to another, for which we basically need these 3 parameters. The driving force energy is the kind of difference in which position the charge likes to sit. But once we're considering only a certain kind of polymer, this one can be neglected because it's 0, because the 2 chains are the same. So what we need to calculate is only the reorganization energy and the coupling element. Let me start with the coupling element. This is a quantity that you need in a lot of theories and a lot of models to describe different stuffs. And the basic equation is more or less, or one can define it like this, which is very complicated to calculate directly. What we need, or what is typically done, is to apply certain simplifications and approximations. And the one that I'm using here is the so-called fragment orbital approach, which allows us to calculate this coupling element based on the HOMO and the LUMO wave functions. And the first thing we might ask is, okay, how does coupling depend on the stacking configuration? So here you see a box of two polymers that are stacked in parallel. And I have calculated this charge transfers, shifting this upper chain on top of the lower one. And the result is shown here with this colored curves. And what we see is that we obtain a very strong oscillation, which we can interpret based on the HOMO and LUMO function itself, because each of these vanishing coupling elements can be correlated with these node surface in this orbital plots. The second thing you can see in this plot is this black curve, which is the energy that we obtain for each of this stacking configuration. And here we see that we have several local minima, so there might be different stable configuration in which the polymers might align. And they are partially separated by very high barriers. So when we think about how the polymers deposit during a process, we cannot say that all of the polymers will align in the most stable configuration. So each of this configuration might occur and it might be impossible to move. So to our opinion, it's not meaningful to just consider a single configuration to predict what is this coupling element. And therefore, we were rather considering a statistical approach where we average over many configurations. And once we are using DFTB here, this allows us, due to its computationally high efficiency, to calculate a huge number of configurations. So it's typically in the order of 80,000 different stacking configurations and average over this. And it's basically a Boltzmann averaging or a Boltzmann weight statistics. The only difference we do is that we substitute the global minima by the local minima, which would represent a poorly annealed polymer film. And if we do so, we can obtain single numbers for a certain polymer orientation. So the system that I showed you before would be a result in these numbers. But we have much more degrees of freedom than just the stacking orientation, because we can also think of that within the chain, the successive units might be oriented in different ways. So for instance, this thiophene points in different directions here. We can also think about this here. And when you think about the stacking, we have a kind of a parallel stacking and an anti-parallel one. So what we obtain is very different numbers for each of these different orientations. So we get a broad variation of this coupling element depending on which orientation we are looking at. What we originally were interested in with this research was what might be the best donor unit for this kind of polymer. And if we can predict, or if we can say, yeah, which is best to use to suggest to chemicists to synthesize. But what we see here is that the variation is more or less the same for all of these units. Next, the reorganization energy. Because of the time constraints we have in this talk, I would like to skip it, even though we find some nice correlations here. If you're interested in, I refer you to the publication about this. I would rather proceed to the final conclusion about this part. So here again, you see the Marcus transfer rate equation. And in this color plot, depending on the reorganization energy and the coupling element, what we would like to have would be big values of this rate constant. And what we see is with all of the materials that we find, they vary over a broad range. So for instance, the circles, which refer to a certain donor unit, they vary quite a lot. And if we use this parameters, this rate equation, and enter in a simple diffusion model, we can conclude on some mobilities here. And we see that most of these values are more or less the same. So the conclusion that we draw from this is that if we would like to design a new material, it's not meaningful to mostly consider this part of the modeling, but rather focus on other properties. For instance, how easy is it to synthesize, how pure it can be synthesized, and so on. Or if you would like to really use those calculations and try to predict the mobility, you need to be able in experiment to have fully control over the orientation within the polymer and the stacking of them. I would like to proceed to the second part. What I've told you right now was something to model and to determine the mobility in those systems. Now I go to something that is rather meant to increase the density, so the charge carrier density. And this is done by doping, which is more or less similar to conventional doping of inorganic semiconductors, namely by admixing some electron-rich or poor compounds. And in our case, these are other molecules. And the challenge that we are struggling with is that this donor acceptor polymer has very low laying HOMO energy, which is something that you wanted originally. But it gives us the challenge that we need very strong dopants to be able to make a p-doping in such systems. To model this, there exists basically two models. One is the so-called integer charge transfer, where you simply compare the HOMO and the LUMO energies of the polymer and the dopant, and you look for something where the LUMO is lower than the HOMO of the polymer, and that this charge transfer can occur. And the other model is the so-called charge transfer complex model, in which you directly consider the complex of the polymer itself together with the dopant, and you calculate the HOMO and the LUMO of this complex model and check how the original compounds contribute to this model. The models for the dopants we have considered here are these three. The left two ones were very well known and used for quite a while already. And this right one was something our experimental colleagues came up with that promised a very strong dopant property. And for the polymer, we again use this DPP and thiophene-based model. This calculation that I'm going to show you later is done as a gas phase model. So we need to cut from this polymer certain models as certain units. And we have done this in separate ways. So on the one hand, we have cut those symmetric parts where this donor or acceptor units are in the middle, or we cut it two complete units out of it. And the results are shown here. So on the left side, in blue, the LUMO of the dopant models, and on the right, the HOMO of this donor acceptor model. And we see that in all of those cases, we get lower LUMOs for the dopants than the HOMO of the polymer. So here we can suggest that the charge transfer occurs for all of those three. And if we compare this to some experimental measurements of the conductivity in those systems, we also get a very good agreement that the strength of those dopants increases, and this Rutile model yields a very high dopant properties. And those days, and I think it's even nowadays kind of record for the conductivity in molecular doped polymers, which is around 70 Siemens per centimeter. Now a few words about this complex model, which we also calculated. Here you can see in this blue shapes how this complex models behave. So we get mu HOMOs and LUMOs, and we have studied mainly two different cases, namely ones where this dopant is localized on top of the donor unit and ones where it's localized on top of the acceptor unit. And by simply using the difference between the HOMO and the LUMO, we can make a first or 0th order approximation of the transition, which gives us these two wave numbers. And this is indeed what the experimentalists observe when they perform some UV-Vis spectroscopy, namely the formation of those bands when they admix the dopant and the polymer. Using this model, we can also calculate the charge transfer using different population analysis. And here we see that we get a larger charge transfer when the dopant is localized on the donor unit than in the acceptor unit, which is kind of expected. Very interesting here is that we still see a charge transfer when we localize it on the acceptor unit, which shows the strong ability of this Rutile model to take some electrons. With this, I come to my third and last part of the presentations, which is now about the transport in the direction of the polymer itself. When you think about this, you can think about two different kind of models to do this. There is also a hopping transport, similar as I have shown you for this intramolecular charge transfer. But there might also be some tunneling process or some ballistic transport, which is more important when you use these polymers or these systems in a kind of molecular electronics, so where you really use just one molecule for the transport, for instance, by putting them between two gold contacts. And for those cases, you expect the conductance to follow this kind of exponential degrees, or this exponential dependence on the length of the molecule. And the characteristic property or quantity one is looking at is this beta, which is the inverse decay length that tells us how fast a wave function decays in the polymer and allows a tunneling process. And this can be modeled by calculating polymers using periodic boundary conditions and something that is called the complex band structure. This figure here on the right shows you in the right part something that you might know already. It's a normal band structure where we have a certain wave vector, which typically takes only real values. By using the same formalism, but only allowing complex k vectors, so k vectors with an imaginary part, we see that in the space where we typically have a gap, we obtain solutions of the Schrödinger equation that closes these two bands here. And there exists a model that describes this loop over here that's based on a two-band model. And this allows to express this inverse decay length by the HOMO and LUMO energies and the gap, which are values that we could already calculate from the normal of the common band structure, but also something that is equivalent to the effective mass. So the effective mass in this band gap. And if we use this model, so I'm now zooming in this part and I square these numbers over here, we see that all of these points form exactly a parabola, which is in agreement with this parabolic function inside under the square root here. And looking at the curvature of this parabola, we can conclude on the reduced mass for each system. And we did this calculation for several kind of molecules. These values that you see here is based on an extended Huckel theory, but since then I have also checked them, or I have implemented something that does this also by DFTB, and the values are in very good agreement, so we can look in these published values for now. So we have studied different systems, but I would like to focus on the ones that use this DPP unit here. And all of these values that we have here are shown now in this graph, where we have this product of the gap and the star and the obtained beta. And we see that the obtained values, they follow exactly this square root function as the model predicts. And all of those models, which are symbolized by this star over here, belong to those who give us very, very small, or the most small betas as we want them. So let's zoom in a little bit in this region. And if we see here, we can look at a sequence of all of these stars. I have enumerated them in case you cannot see the colors very well. And if we compare this to the model for which we have calculated those values and compare about the individual modifications we did on the structure, we see that in order to minimize this beta, so we need to maximize the donor and the acceptor strengths to get the lowest values here. So in the case where we have this thienothiophenone here and the diketopyrrolopyrrole, we get a very low value here. Okay, with this, I'm in the end of my talk. Let me quickly summarize. So I showed you something about the charge transfer and the molecular doping. And finally, I told you something about the conductance tunneling regime, where we mostly found that the donor acceptor strengths, with the increasing donor acceptor strengths, we get the high decay lengths. Yeah. And with this, I finish. I just would like to thank my collaborators, especially my supervisors for my PhD and the collaborators from the experiment. I thank my funding resources and very much all the organizers for preparing this colloquium and managing it. And last but not least, of course, all of you for your attention.
Thank you, Florian, for the nice talk on these functionalized polymer systems. And the floor is open for questions. No, well, again, please keep the eyes on the chat. I would like to ask you, actually, how is the choice of the dopants done? The choice of the dopants in the sense to match the desired HUMO and LUMO desired parameters.
Yeah. So there are different properties based on which the people decide which ones are to use. The most important one is to have something that is very electron efficient, so accepting. And what you need for this is, in principle, those functional groups like this cyanoprop over here that takes a lot of electrons from the core over here, that when you put this on top of the polymer, it takes the electrons as you want, right? So what you need is something that has some local dipoles. So there's also this fluor that you can typically use for functionalization. This is the basic idea, but chemists in the end, they also need to focus on what they can synthesize. So it's more the practical choice to check what they are able to do. So it's kind of finding the balance between something that, okay, in principle, it should be this, what we can synthesize, and then, yeah.
I understand. Yesterday was an interesting talk about this, but exploring machine learning techniques for choosing the most appropriate dopant for, yeah. I think it could maybe eventually be applied also in these kind of situations. But of course, experimental results rules, right?
Exactly. So I am a little bit, so I think I share a lot of the opinion that Carsten Reuter showed us in the morning today. I'm also very suspicious about this, but yeah, it could be an idea to check, to do those kind of simulation or to do this kind of research, to combine it with machine learning. But I think the hard part, even though that the machine learning may suggest you a certain structure, the next question is if you can synthesize it.
That remains the final challenge, indeed. Let's continue the debate on the chat. Thanks very much. Looking forward to follow the debate on the next sessions and so on. And we have to move forward to our next speaker that is coming from Shanghai, China, Dr. Jiang. Am I correct? If I pronounce it wrong, please excuse me.
Yes.
Yes? Okay. Please have the floor.
Okay, can you see my presentation?
Yes, yes. Everything is in order. Yeah.
Okay. Hello everyone. I'm Kaiyu Jiang, coming from Shanghai Jiao Tong University. I'm very glad to be here. Today I want to talk you a heterostructure based on the ruthenium molybdenum nanoalloys as an electrocatalyst for hydrogen evolution reaction. First, I will start with a brief introduction and motivation for why we designed this material for hydrogen evolution reaction, and what are our goals in this work. Then turn to the experimental and simulation results, including material fabrication, theoretical model construction, and how both results can fit each other. At the end, I will conclude my results. Okay, start with the introduction. We know that the hydrogen gas is an important energy source because it is renewable and clean alternative for fossil fuels. It is mainly employed to produce ammonia and to refine oil. also for hydrogen-driven vehicles. So how to produce the hydrogen gas? Water dissociation driven by renewable energy sources is the most feasible process. Here you relate two methods for hydrogen gas reduction. One is water electrolysis and the other one is solar hydrogen production. In these slides, some related devices are shown here. The electrochemical cell, which is typical device, is composed by the two electrodes, the anodes and the cathodes. On one side, oxygen gas is released, and on the other side, the hydrogen gas is produced. The difference among different electrodes is known as overpotential, which can be used to evaluate the electrocatalytic properties. And people are looking for the more efficiency catalysts with a lower overpotential. And now it is known that platinum-based materials are regarded as the most suitable catalysts for the water dissociation. But due to its high cost and scarcity, other cheaper materials are having more interest from people. For example, the family of the ruthenium-based materials. In some recent researches, some researchers synthesize ruthenium absorbed on the platinum cone shell nanoparticles, and or the allying transitional metal atoms such as cobalt or nickel atoms into the ruthenium lattice. And in their reports, both the simulation and the experimental results show that this preparation methods leads to an increasing activity towards the hydrogen evolution reaction. But however, synthesis of the ruthenium-based nanoalloy particles with the controlled morphology and good stability is still challenging. So we are looking for the proper substrates. Introducing conductive substrates will not only solve the problem of the stability, but also the morphology control. So among all those conductivity substrates, we have chosen two-dimensional porous carbon nanosheets because it is distinguished with these three advantages. The thicknesses of nanometer and interconnected pores, and also a long range conductivity and chemical stability. So for our goals in this work, first we combine the 2DPC with the ruthenium molybdenum alloy to excise the target heterostructure materials. And then we want to get an insight of the hydrogen evolution activity assisted with the Dft calculation. Here is the fabrication process. Our materials is named ruthenium molybdenum nanoalloy embedded two-dimensional porous carbon nanosheets, 2DPC ruthenium molybdenum nanosheets. As the process demonstrated here, the layered double hydroxides were used as sacrificial templates, and the cationic polyamides were the precursors, and the metal containing anions was a key metal sources. In short, the 2DPC ruthenium molybdenum nanosheets were obtained after these 4 steps. The first is the polymerization, and then the anion exchange process, and then the pyrolysis, and finally etching. To detect the chemical structure, in these slides, we can see from the results of the EPS-CMD and EXEFS spectral, the ruthenium bonds and the ruthenium molybdenum bonds are clearly observed, and no molybdenum bonds inside. And from the TEM image, the morphologies are maintained after pyrolysis. And also from the further characterizations, surface ruthenium-101 is found the dominant surface exposed. So based on all the chemical structure characterization, we made our models for this hydrogen evolution reaction calculations. In the simulation part, Dft calculations were performed by WASP. All the systems extend periodically in X and Y direction and keep an vacuum space in Z direction. Due to the size of our structures, very big, approximately 300 atoms, only one key points has been used, and free energies have been calculated using the NOSCO model. The energy and frequency values are from the WASP results, and the temperature and the entropy values are from the literatures. Here is showing the 6 different models we have made. The first one is the pure graphene absorbed on the ruthenium surface, and the second one is graphitic structure absorbed on the ruthenium surface. And then we built the pyridinic structure with 3 or 4 nitrogen atoms absorbed on the ruthenium surface. And we also made the models with the molybdenum atoms doped in. So due to the ideal GEFES free energy of the absorbed hydrogen atoms is supposed to be close to 0 from the viewpoint of thermodynamics, we first use the Dft calculation to evaluate the free energy of the hydrogen atom absorbed on the surface. Here are the free energy results. From the first table at the right side, graphene type surfaces which performed 1.75 to 0.08 or minus 2.02 or minus 1.35 EV are not good. And the pure ruthenium 101 surface with minus 0.74 EV is not good enough also. And then we calculate the surface structure which combined those 2 types of structures, and the free energies are listed at the second table. It is obviously that after introducing the defects with pyridinic structure and the doped molybdenum atoms, the free energies are quite improved. In our simulations for calculating each pyridinic structure absorbed on the ruthenium surface doped with molybdenum atoms, we considered the influence brought by the different active sites. From the table at the left side, we could say that the most favorable free energy for this structure is approximately minus 0.18 EV. With the type of structure, nitrogen size B and molybdenum size E, which is exactly shown at the bottom of the right side. Also, we did the same calculations to the pyridinic structure with 4 nitrogen atoms absorbed on the ruthenium surface. From the free energy table, we could say both the molybdenum size A and B are favorable with much lower energies than others, but for the other active site C, which is not good, the most likely reason is that no molybdenum atom located at the first layer of the ruthenium surface, so it cannot cause a good interaction with the absorbed hydrogen atoms. Then we have the experimental results from our colleagues. From these results, which are shown here, the 2DPC ruthenium molybdenum material is showing a lower Or potential and a smaller TOEFL slope than the related materials we have tested here. These results are in a good agreement with our calculated results. And compared with other ruthenium-based hydrogen evolution reaction catalysts in alkaline solutions, this material shows a good performance. Here, I'd like to give a brief conclusion. In this work, we fabricate carbon mantle heterostructures both the simulation and experimental results performed that the material could be a promising electrocatalyst for the hydrogen evolution reaction. Here I want to thank to Professor Xiaodong Zhuang for his support, and thank to Dr. Diana Chanka for kind help and advices, and also thank to my colleagues. Finally, thank all of you attention.
Yeah, thank you, Jiang, for the nice presentation. We have time for short questions. You are very well on time, so thank you for that. There are some questions on the chat, and these are: how stable are these materials in solution?
I didn't put the experimental results in this presentation, but the results are from our colleagues. I have heard that it is stable in the alkaline solution, but I didn't remember the details of the cycle results or others.
Okay, another question is: are these structures experimentally possible?
What do you mean the?
These proposed structures are experimentally possible, probably related to the doping structures that you have shown.
We actually tested, I mean, we make our model system considering the experimental results that our colleagues did it. So they are actually possible.
Okay. No, that's yeah. It's a thank you. It's a the participant is happy with the question. We have thank you very much. We have to move forward. I let the chat space for yeah, it is another one. Are these structure no, that's it. Probably the debate goes on in the chat. Thanks a lot. We move forward to our the floor is yours.
Good day, everyone. Thank you for accepting me to have this talk. So the overview of the atomic scale simulation for oxygen evolution reaction was performed also with the aid of the group from University of Copenhagen, the Jan Roos-Meisel group, and with the aid of Jonas Kanka from Eindhoven University of Technology. Whoops. No, it seems it doesn't work. What?
If it doesn't work in the presentation mode, just proceed with the slides, I would say, but it's just an idea.
Yeah, you can also just go with the slides. Yeah, that's also fine.
It's all fine.
Okay. Okay, so the idea is also related to energy, to going energy friendly and to produce hydrogen in a sustainable way. This time, compared to the previous presentation, the focus is on the anode side, where the oxygen evolution takes place, or water oxidation. The problem is related to the fact that the catalysts, even the best ones, give very relatively high overpotentials, and this decrease the efficiency of the entire cell. The other problem related to the catalysts are the ones is the fact that they are quite expensive and scarce. So therefore, there are efforts to to find and to design catalysts using earth abundant materials. From theoretical point of view, we try to find descriptors in order to reduce the calculation time and to screen more materials, such as to make approximations for which are the best ones, such as to reduce the number of tested materials. Along the time, different descriptors were used and defined in order to screen the materials, such as the electrons of transition metals. This is a very old search from '84, and then OP band center or occupancy of the EG bands, and also absorption energetics. In the following part, I'm going to focus on the descriptor based on the absorption energetics. How the derivation of this absorption energetic descriptor is based on the fact that the primary effect in electrocatalysis is based on the bond strength between electrode surface and the reaction intermediate. The model is based on the associative mechanism of water dissociation, in which takes place in 4 steps with formation of 4 electrons and 4 protons. And the intermediates that are formed are OH intermediate, OH intermediate, or oxygen intermediate, HOO, hydroperoxide intermediate. And here, yeah, it's a little bit small. The reaction path is the dissociation of water with the formation of 1 proton, 1 electron, then the loss of 1 proton and formation of oxygen, the dissociation of the second water molecule on top of the formed oxygen, and with the formation of hydroperoxyl fragment, and then deprotonation of this fragment and release of the oxygen molecule. For each intermediate step, a free energy it corresponds, and is based on the absorption energies of the intermediates calculated from DFT energies. The effect of the potential in the free energies provided by the term minus EU, and the effect of pH with the second term. Here is the way the free energy are calculated with the aid of the DFT energies. So the DFT energies are also added the 0-point energy and the entropy correction. Moreover, other approximations that are introduced in the model is the computational hydrogen electrode, which at standard condition pH 0, 1 pressure bar of the hydrogen, room temperature, 0 potential, the chemical potential of protons and electrons is equal with half of the chemical potential of the hydrogen in the gas phase. The liquid water is also approximated with the potential of hydrogen in the gas phase, also at room temperature, but at 0.035 bars when this equilibrium takes place. In order to derive further the model, the free energies are calculated without taking into account any value of the pH, only 0 pH and potential 0. So all the free energies are reduced to the absorption, the free energy, the absorption free energies of the intermediates, and then the d over potential is maximum of the fourth free energies minus the equilibrium potential at standard condition. What we can observe from these two graphs is the fact that the free energies are endothermic at zero potential. When the potential is increased, then the free energies decrease. At the equilibrium, for most of the catalysts, they are still endothermic steps. Herein, we go further with deriving the descriptor. So 10 years ago, we derived the descriptor based on the scaling relation between the free energy, between the binding energy of hydroperoxyl fragment and hydroxyl fragment, which for all across the the absorption energy of the hydroxyl absorption energy, there is a constant difference between these two bindings. So this relation is used in the free energy relation, in the previous free energy relations. On the other hand, the variation of oxygen binding energy is 0.5, has the slope of 0.5, and we based on the fact that most of the studied catalysts have the maximum free energy either G2 or G3, which is the deprotonation of hydroxyl fragment, or the dissociation of the second water molecule. So going further, we reduce the descriptor to the difference of the two free energies of the oxygen and hydroxyl fragments, and also we have this intercept that we obtained previously for the scaling relation between the hydroperoxyl and hydroxyl fragments. What I want to emphasize is the fact that for the ideal case, this scaling has to be correlated with 2.46 eV, because in the ideal case, all the free energy steps should be 1.23 eV. So here I just want to show, it was an how I say animation, but doesn't work. Okay, I will just go further. Is the fact that the differences between hydroperoxyl and hydroxyl keeps constant while going up or down with the binding energies, but the level of oxygen varies much faster in between these two levels. So volcano plot was performed with the aid of this descriptor, and its validity is was checked by the aid of the experimental overpotential, and the results were quite satisfactory. And since then, this descriptor was used in quite a large number of articles for different oxide materials. Even this year, it still use this descriptor. So therefore, we just said, let's see how the scaling holds for a larger number of data points. Therefore, we have collected data from 25 articles, the there are even more articles, but we just stopped to these ones, and we perform a new scaling. It holds, the scaling still holds, but with higher mean average errors. As can be seen, the oxygen points are very scattered in between these two levels. And I'm going to show further analysis to try to understand the variation of the oxygen levels in between these two levels. The volcano plot was redesigned, and once more we can just see the points that are across the volcano legs. And here, for example, I have divided the overpotential in domains, and therefore these points could be just, these materials could be just further tested or so on. Here, as I said, I have tried to split the data, and the way we have done it, we have divided the data according to some overpotential domain. We have chosen from 0 to 0.6, from 0.6 to 1, and overpotential higher than 1. And we can just observe that some trends are also available for oxygen levels. So in this case, the slope is equal to 1. For the data that are that have the smallest overpotentials, then when we go to the second overpotential domain, also trends with linear slopes are available, but with points that are divided in two domains. One, the points that are closer to hydroperoxide adsorption energies, and the points that are closer to hydroxyl energies. One can just see also for example, for the points from the lowest overpotential regime, the absorption energy for hydroxyl is limited to a certain domain. It's relatively large, between -0.5 to 1.5, so it's within 2 electron volts, but not towards lower and higher absorption energy. For the second domain, once more, this domain extends a little bit, but we don't have any break, for example, in the middle. The same is valid for the last overpotential domain, with points that go closer to OH or hydroperoxide fragment absorption energy. On the other hand, here is just an idea. Of course, it has to be checked further on. For example, for the same absorption energy of hydroxyl, the absorption energies of oxygen for different materials are varying in a range of approximately 3 electron volts. So therefore, OH binds similar on all materials, while oxygen, the absorption energy of oxygen differs and is made different from material to material. The idea it is that everything looks nice, and but there are also problems related to this the scaling relations among the data that are in the scaling relations. There are also more data obtained for the same materials, but with different functional, different softwares, and this could lead also to large errors when going from one to the other. We know that ruthenium dioxide is a good catalyst, so normally we should obtain a point closer to the top of the volcano. So care should be taken when the method is chosen, such as to have a reliable prediction of the trends. The idea is that these oxides are quite have a quite complex electronic structure. Therefore, even now there are still problems to choose the right functional method, such as to have a fast screening of the materials. Probably you can go to hybrid functionals, but they are very costly. So it's there are various problems still related to screening these materials. Another aspect that I want just to show, also related to choosing the functionals, is related to doped TiO2 rutile structure. And yeah, no, the points are very small. I don't know, can you follow?
They are very small indeed.
I will try to go on.
I ask the points maybe to yeah, or simply tell us where to look. Yeah, that's much is better. Yes.
Okay. Yeah. I have choose from the articles the doping elements that give an extra electron. So vanadium, niobium, tantalum, and extra 2 electrons, chromium, molybdenum, wolfram. In this case, in the 6+ oxidation states, they could have as well other oxidation states. So the trend might be, it's a little bit off, but what can observe is that the absorption energy of oxygen when one extra electron is in the system, it's weaker than when 2 electrons are in the 2 electron dopants are in the matrix. The idea, and this doesn't matter where the dopant is placed in the surface, either in the bridge positions or cast position, or in the second layer beneath the first layer. So approximately the same relation is established between these doping structures. Here is it in the D graph. The unit cell was increased, and also the number of dopants were increased. The idea is the same. So the ones that have 1 extra electron binds oxygen weaker, while the ones that have 2 or more extra electron, for example, in the case when there are 2 molybdenum atoms, then it should be 4 electrons, but they bind stronger. Another observation is the fact that, for example, OH binds with the same strength on the 1 tantalum or 2 tantalum atoms. So this is related as well to the fact that OH and OH need 1 extra electron to perform the octet configuration, while oxygen needs 2 electrons to perform the octet configuration. So therefore, when 2 electrons are provided by the doping elements, then oxygen fulfill the full octet configuration, and that's why we believe that it binds stronger when compared to the case when only one electron is provided to the system. And here it's evidentiated the shift of the Fermi level when one vanadium, for example, one vanadium is doping the system. The Fermi level shifts from it's at the conduction band. Then one hydroxyl is absorbed, the Fermi level shifts to the middle of the band gap. Then one oxygen is absorbed, then the level shifts to the valence band. When two vanadium atoms are present in the system, I'm just going to show the difference between absorbing of oxygen on these two systems. So in this case, the Fermi level is at the middle of the band gap. The idea is that in the first case, the oxygen probably takes the extra electron from the surface. And in the second case, the two electrons are provided by the vanadium atoms. And the chemical potential of the two electrons is different. Therefore, the shifting of the Fermi level. Further on, I want to show approximately the same behavior of the shift of the Fermi level when there are only coadsorbents on the surface and not dopants. Coadsorbents that behave as acceptor donor fragments on the semiconductor surfaces. So it's the case of hydrogen and absorb on the oxygen fragments from the surface, and hydroxyl that absorb on titanium side of the surface. When oxygen absorb on the titanium surface, the Fermi level shifts from the middle of the band gap towards the conduction band. So this hydrogen gives one electron to the surface. When OH is absorbed on the titanium side, then the Fermi level goes towards the conduction band. When they are together coadsorbed, then the Fermi level stays at the middle of the band gap, as in the case of the clean surface. Here I came with another example. The same is for perovskites, the same behavior. So we tried to extend this observation to more oxides, and we have found a connection between the absorption energies and the band gap. Here it's actually a difference between when the fragments absorb alone in the unit cell and when they are coadsorbed. When they are coadsorbed, they absorb stronger, and this stronger absorption varies with the value of the band gap for the semiconductors. In this part, in this region, there are the conductive surfaces, ruthenium and iridium oxides, they are conductive elements. So in this case, no difference in between these two types of absorption energies is observed. Once more, we have tested.
Can we hurry towards the conclusion? I see Daniel is looking forward to give his presentation.
Okay, what I want to just to emphasize.
Just a small warning. Yeah.
Okay, I just want to draw the attention that we have tried to improve the description of the electronic structure of the TiO2 by applying the Huber correction for the d electrons, and this scaling relation for oxygen changes quite drastically. So therefore, I wanted to emphasize the fact that it's very important to how the functions and methods are chosen in order to have a proper screening of the materials. Here I go to conclusions. The scaling relations between the hydroperoxide and hydroxyl fragments still holds for a larger set of oxides, but with a larger scattering. The descriptor is still feasible to a fast screening through the catalyst to provide catalyst theoretical activities. A better scaling relation between the level of oxygen and hydroxyl is obtained when the data are divided using the overpotential domains. Of course, there are issues concerning the choice of the proper method that could be applied to various types of oxides, such as to provide accurate absorption energies in a cost-effective way. So this issue still exists and still probably will exist for the next years. And aspects to explore in the future, try to apply different strategies. For example, to understand the large variation of oxygen absorption energies for materials that have the same absorption for the hydroxyl. Try to find correlation between the shift of Fermi level inside the band gap and the band gap value. That can be an explanation of part of the variation of absorption energies. Thank you for the.
Thank you, Isabella. There are quite some questions on the chat. I will put one, maybe with the other one we proceed on the chat. I also have some questions that I will not put here. Would calculating band gaps via DFTB be an option? It is often said that DFTB gives better band gaps than DFT.
Yes, the question it is, we need a method and that provide a good description of absorption energy and also of the band gap. I'm not familiar with DFTB, so probably you know better to tell us if the absorption energies are also described well with DFTB. So it's a kind of because even for hybrid functionals, I think there are still problems with describing both properties well in the same time.
In the audience, questions to be put now online verbally to Isabella before continuing, of course, on the chat. I have a few questions for you, Isabella, but I will put it on the chat in order not to take the space of the others.
Okay.
Any
may I?
Please, please.
I hope it's quick. I don't know if you mentioned it because I couldn't follow everything. It's one more technical question. So what software you're using and functionals and so on?
So all the data that were gathered in the big picture are from different papers that are dealing with different functionals, different softwares. The software I have used for TiO2, the last slide, just a moment.
So do you know something about basis set superposition error when using local basis sets?
No, I cannot. Most of the papers are done using plane wave or.
Okay, I see. I see. You don't have this problem. I see. Okay.
Yeah.
Thank you.
You're welcome.
Thank you, Thank you, Isabella. Thank you, Florian. I think we can continue the debate online in view of time. Thanks, Isabella. See you on the chat. I would like to go further and introduce our next speaker, Daniel Bahamon, from a joint collaboration, Khalifa University and Aliatech. I don't know, Daniel, where you are at this moment, in a skyscraper or in a nice beach in Spain. But we are definitely going to talk about carbon-based membranes for water purification. That we know for sure.
Thank you. Thank you, Silva. Can you hear me?
Yes, I can hear you. Yes, yes.
Okay, perfect. Let me share my screen. Is everything correct, no? So thank you very much for the nice introduction. Right now, I'm in Abu Dhabi, in the United Arab Emirates. It's a bit warm outside, around 40 degrees Celsius, but inside, in the office, is fine.
It's always too cold inside.
Exactly. So today I will be talking about, yes, as you were mentioning, novel carbon-based materials for water purification. This is an outline of my presentation. I will explain part of the motivation of this work, the research strategy we are using. I'm going to focus on two different case studies in the results and discussions. The first one devoted to graphene oxide membranes for the pollutant removals, and the second one for a hybrid graphene oxide membranes, and in this case for water desalination. And I will finish with some conclusions and some acknowledgements. So in the motivation, as we know, the scarcity of fresh water represents a serious global challenge, no? And is predicted to be worse in the future owing to the climate change and the increase of the population. And moreover, there is also an increased concern related to water production, pollution due to these recalcitrant contaminants named pharmaceuticals, phenolic compounds, because these organic compounds, these organic molecules, are in very, very small concentrations below ppms in these effluents, in this fresh water. They are very difficult to biodegrade, and much of the potential impact on the environment and on the health of the human health is completely unknown. So there are many different techniques to remove these pollutants from water, like advanced oxidation, electrodegradation, ultrasonic irradiation. In our case, we are focused on membranes, as you can see. Membranes can be constructed with inorganic structures like microporous silica zeolites. They can also be synthesized with polymers, which is basically the benchmark right now for reverse osmosis. And we are dealing with carbon-based membranes. Carbon-based membranes, in specific, graphene and graphene oxide membranes. Why graphene and graphene oxide membranes? Because, as you know, graphene is a material with a high mechanical and chemical stability, high mechanical strength and chemical stability. Is thinner, so we can reduce the pressure drop across the membrane. And moreover, the graphene oxide is very cheap. It's cost energy efficient, so it can be synthesized by exfoliating graphite. So it can be used at a large scale. It has similar characteristics compared to the graphene, and can filter ions and can be tuned according to the requirements of the process. So for the research strategy, we are basically synthesizing and fabricating these hybrid graphene oxide nanostructures. And we are also combining this with molecular simulations in order to understand the underlying mechanism of such hybrid nanomaterials, to evaluate the different phenomena that are occurring inside the membrane, like size exclusion, electrostatic interactions, ion absorption. And in the talk I'm giving today, so I will explain part of the results with the effect of interlayer spacing, the intercalation of the graphene oxide sheets, and some results devoted to water permeation and pollutant rejection under typical process conditions. So let me start with the first case study. In this study, we performed some simulations for graphene oxide membranes for difference, and it was devoted for pollutant removal. We started by constructing a graphene oxide membrane with graphene oxide sheets, and we used non-equilibrium molecular dynamics in order to evaluate how the molecules are passing through the membrane. No? We evaluated different oxygen concentrations for the membrane, and we also evaluated the number of layers in the membrane. And as you can see here, we have basically the configuration of our membrane. So the molecules are passing first on top, then on the right, then on the lower part, and then on the left. This is the configuration we have for this membrane. And moreover, we assure that the interlayer distance in this case is for this non-equilibrium molecular dynamics. We were using NVT ensemble. We fixed the interlayer distance of the carbon atoms, but we allow the oxygen and hydrogen molecules to move freely across the membrane. And we did this study for, as I was mentioning, phenolic compounds and also some pharmaceuticals as like ibuprofen. For the first results, I'm showing here this is the density profile. These are the density profiles for water for the different membranes we constructed. In the first one, and on the left side we have only one graphene oxide layer. On the second one I have two, and I have four on the right hand side. And as you can see, this is for three different concentrations: pure graphene, which is the blue dashed line; reduced graphene, which has a lower oxygen concentration on the structure; and graphene oxide, which can be commercially available, which is around 30–35% in weight of oxygen. And as you can see from the plots, from the density profiles, as you increase the oxygen concentration in your membrane, you have more affinity. The water molecules have more affinity for the membrane. So you have like an increase in this density at close to the different sheets. We also study the same, but in this case I'm showing here the radial distribution function for the different molecules we studied. And it was interesting that we found that depending on the type of molecule we have, of course, because we have steric effects here, and the type of organic of these organic compounds, we have the closer are the interactions between the OH from the graphene oxide membrane and our molecule. In this case, ibuprofen for sure has closer interactions than phenolic compounds. Oops. And these are the other results regarding the performance of our membranes. And on the left-hand side, you can see this is basically what you can obtain from the non-equilibrium molecular dynamics, is the number of water molecules passing through the membrane. So we are tracking the number of molecules, of water molecules or organic compounds passing as a function of time, no? And as you can see, as we increase the number of layers in the membrane, we are reducing the flux, no? The number of molecules that are passing, and is a monotonic decrease. Moreover, if we see the performance in terms of rejection, of permeability of our membrane, as you can see here, as we increase the number of layers, for sure we have lower permeability because it's related to the flux. And we also have, by increasing the number of layers, we also can increase the rejection rate. So as you can see in circles, we have one layer with the rejection for these organic compounds is around 50–60%. And if you go to 4 layers, you can achieve rejections of 100 in our case, 100%. Let's move forward to the second case study. In this case, we are focused on these hybrid graphene oxide membranes. And in this case, the application was water desalination. And this is part of our project we are conducting in collaboration with the Korean Institute of Science and Technology. And in this case, we also have experimental results, as I will show you later. So the basic idea is we have these graphene oxide sheets, but the problem is with the swelling, with the water, they will swell, no? So we have to tune the interlayer distance in order to increase the flow of the water flow and reduce the rejection. and increase the rejection. So in this case, we were using these crown eaters, which are basically organic molecules that can tightly bind different ions. As you can see here on the left-hand side on our table, they can tie sodium, potassium, cesium ions, and we can tune the interlayer distance of our membrane. From the experimental results, what we did first was to do an SEM of different membranes with different crown eater concentrations, 5, 10. Well, this is in concentration. More details in the paper here. And as you can see, as we increase the number of intercalated crown eaters, the thickness of the composite will increase, and the smoother the membrane will be. And we can see here on the right hand side that, of course, as we increase the number of crown eaters, we can finely tune the membrane. And as you can see, we are reducing this degree, this angle, and that means that we are reducing the angle. So that means that we are also increasing the interlayer distance between the two layers. So we have to play for which concentration should be the most appropriate one. And in here, as you can see here on the bottom, we have the results for the water flux and salt rejection. And as I was mentioning, by increasing the concentration of the crown eaters, of course, we can increase the rejection rate for this, in specific for this salt. But we will lose some permeability of our membrane, because since this is more broad, the molecules can pass through the membrane. We try to understand this with molecular simulations. In this case, we perform some equilibrium molecular dynamics, trying to evaluate the interlayer distance and the energy of absorption of these specific organic compounds, crown eaters and ions in the membrane. And as I'm showing here on the right-hand side, we have the absorption energy for different conditions in vacuum, with different concentrations for the crown eater and for the ion, for potassium ion in this case, and also including the ion inside the crown eaters. And as you can see, we can increase the absorption energy of the ions by using the crown eaters. That's very interesting. And more interesting is that we can tune the material, and we found very similar results than in experiments by using these crown eaters intercalated. This crown eater intercalated in our membrane. We found interlayer distance around 11.5 12 angstroms, and before it was 10.5 to 12 angstroms. So very similar. But our problem here was the following. So since we are only calculating this for a very thin membrane, we couldn't compare the experiments for the rejection and the permeance, since we have like 2 orders of magnitude higher water fluxes. And of course, they have in experiments, they have the graphene oxide with the intercalated crown eaters, but they also have a substrate. So we have to increase the number of molecules we have in our simulation, and the difficulty as well. So to summarize, I would like to say that we can use these molecular dynamic simulations to evaluate different structures characteristics of these graphene oxide membranes. I have shown here 2 different studies, case studies, one for pollutant removal and the other one for water desalination. And these models are sufficiently flexible and can be tuned for different, their parameters can be easily tuned to include additional features. In specific, for study number 1, we found that the role of the surface is very important, because we can enhance the absorption, the rejection removal, and increase the water flow by tuning these the number of the concentration of the oxygen in our graphene oxide membrane. And in specific for study number 2, we obtained we saw that our simulation results are consistent with the experimental values, but still there is a compromise between the two different properties we were calculating, the permeability and the rejection performance. And there is still there are several challenges still to merge both works, the simulation part and the experimental part, because in the experimental part we still have so many features that we cannot include in our simulations. But at the end, I think that we are progressing, and this is still working in progress. So at the end, I would like to thank you, all of you, for your attention, to wait until the end of this talk. Gracias, shukran in Arabic, and all of the organizers of this very nice conference and the fundings of this project. Thank you very much.
Thank you very much, Daniel. I would give the floor to questions.
Hi, this is Conchania. I have a question, if I may.
Yes,
yes.
sure.
Yes, thank you for the nice presentation. I'm not sure I understood how you actually model your graphene oxide, because I kind of see that you use the ratio of carbon to oxygen, but do you incorporate also the nature of the functionalities?
Of the different oxygen?
Yeah, different oxygen groups in the graphene oxide.
In this case, I only have hydroxyl groups. Yes.
Okay. Yeah, because this is one of the challenges at least from an experimental point of view, that we have a mixture of hydroxyl, also epoxide, which are not very stable, and also you can have carboxylic acid and so forth. So I was going to ask you if you know which one of those groups would be more efficient for your applications.
This is something we are still working on, because yes, in fact, the stronger the oxygen group you have, the better the rejection will be, but the lower the water flux will be. So it's like a trade-off. We are still working on it, but very nice comment. Yes, thank you very much.
Thank you.
Other questions?
For water desalination, you could actually try to apply an external electric field to improve the ion separation. I would imagine this could help essentially in efficient separation. Did you consider this?
Sorry, the what? Couldn't hear you well.
Okay, maybe I can. Could one use an external electric field to improve for water desalination? Because that's something which I would imagine could certainly help ion separation.
Yes, indeed. In fact, we are now working with a different type of membrane that I didn't show here, in which we are trying to include this electrical field and see if we can improve the rejection rate. Yes.
Good. Yeah.
Now still room for final questions, if it is. No? Then also in view of time, because we passed, thank you, Daniel, for the nice presentation. You'll be able to find Daniel on the email address mentioned in the abstract, I think, for additional questions. I would like to thank you all very much for this intense but inspiring and very learnful morning with very interesting presentations. Thanks for your input and for the enthusiasm. And of course, I take on me all the delays that were coming, but thank you for the patience and for staying here until the end of the session. Looking forward to see you all back. I will give the floor to the other organizers to see if there are any important messages still to be passed. I'm looking at your notes now, if there are any important messages still for...
No, I don't think we have, and I would like just to thank you together with you and our organizers, to everybody which participated for very educative and interesting talks. We'd like to encourage you, of course, to stay tuned with the CMD conference, farther on, because there are also other colloquia which continue up to the end of the week, up to Friday. So please try to visit also other colloquia. Our colleague will put online the recordings from yesterday and today, where people have given their agreement. In 1 or 2 cases, we didn't receive the agreement, but we discussed with you privately and you agree, and we are going to send you in the afternoon one more time the file or the link towards the file to give us the agreement. And then the videos will be put only privately towards the members of the conference, so they will not be shared with the whole world, but only within the community. So everybody can go there and maybe see if you missed a talk or if you couldn't see it fully. Recorded that talk. Only for the last 2 days. The first day was not recorded. I think that's all from our side. We thank you very much all for the participation. I would like also to thank Juan, which takes care of recording in Spain and help us so much with Zoom. We hope you enjoy further on the conference, and why not, let's try to stay in touch, because I think we learn each of us one from another quite a lot in these last 3 days. Thank you very much to everybody.
Thank you. It's hard to say goodbye, but let's say that see you soon in the next coming opportunity, and we stay in touch. Thank you.
I hope so. Thank you.